Shortly, we are waiting for our director, sir. He will be joining us maybe within a very short time. So
Okay,
we just
no
wait.
problem. Sure. Mhm.
Okay, sir. Good morning, sir.
Morning.
Good morning.
Hello, good
So-
morning.
Yeah, good morning, Saddev.
Here, I, on behalf of organizing committee, would like to thank Professor Kallanmoy Dev for joining us and accepting our invitation. We have with us Professor Shivaji Bandyopadhyay, sir, Director NIT Silchar, and other distinguished faculties and participants from different parts of India through virtually. I would like to request Professor Shivaji Bandyopadhyay, sir, to share a few words to welcome Professor Kallanmoy Dev.
Yeah, a very good evening to Professor Dev. In fact, in the last December, we were waiting for you to come to the NIT Silchar. Yeah, but anyway, that could not happen. And I think when we look into the effects of the current pandemic situation globally, say people, if the situation makes us depressed, but at the same time, we understand there are some positive issues as well. People are trying to optimize the situation and trying to make the best out of it. And just to give a brief idea, because you belong to this northeast part of India, your origin. Yeah, so obviously, but to have an idea that currently National Institute of Technology Silchar is placed in the 46th position among the engineering colleges in India by the NIRF ranking, and then in the overall ranking of the institutes, we are in the 94th position. And we have a green, large green campus, and it would have been nice, say, when you will be able to visit us. And I do believe that in the coming years, when the new normal situation stabilizes, so we'll be able to have you among us and interact. Now, in the last few years, we have put research and innovation as the key focus of our teaching learning as well as our research activities, because the world, that is the learning or teaching learning activities from a rote learning, it is basically quickly say switching to the inquisitiveness of the mind, that is nurturing that, and so that people or the society can learn more and more things, be inquisitive also, so that that is keeping the research focus in mind. We have for the undergraduate students also, we have undergraduate research council, where we focus the research culture, research participation among the UG students, and many of our undergraduate teams, they have performed very well at the national level, and they have very good research publications as well. So that we are hoping that NIT Silchar will be able to make a niche in the world scenario with the research mind of our students, and we keep the sustainable development goals of United Nations in all our endeavors. Whatever research objectives or research works, research proposals we take, we keep that in mind, so that we can serve the society or our stakeholders, our students, scholars, and that is why we are increasing the number of PhD students also, so that every faculty have got the students to work, and at the same time, interdisciplinary nature of research, so that there is nothing specific like say mechanical or CS or EC or electrical, but whenever you study or you do any inquisitive study, research, etc., it is truly interdisciplinary in nature. And the current conference CoMSO is basically a testimony to the fact that where our colleagues from mechanical and CS and EC, so they are joining hands together and obviously organizing such a program. So learning from each other, and so that is also one of our goals. So with these objectives, we are eagerly waiting to listen from you. And I was in the morning looking through your presentations also. Say it is basically wherever sphere we work, we study, we try to understand. Optimization is the key. We cannot lament that is the resources are not there or less. But the thing is that we should focus our mind on optimizing the resources so that we can achieve our target for our goals. So thank you, sir, and we'll be waiting for your talk with us.
Excellent. Thank you very much for talking about NIT Silchar. As you said, I come from Tripura. I did my schooling in Agartala, and then from there I moved to IIT Kharagpur for my undergraduation, and then after that here and there and all that, finally I finished my PhD and went back to IIT Kanpur, and I was there for 20 years at the mechanical engineering department there. So most of my work in optimization I started with the students and my colleagues over there. And then about 8 years ago, I moved to USA, to Michigan State University, where I am currently holding the Koenig Endowed Chair Professor position at the Department of Electrical and Computer Engineering. I also have a position at the Department of Mechanical Engineering and Computer Science and Engineering. So here's my email address. So I want to make sure that, let me see if this is working. Yeah.
So it's working.
Make sure that you are seeing my slides and also my laser pointer. Yeah?
Yeah.
You're able to see that. Okay.
Everything okay.
Yeah, that's great. Okay, so
Professor Kallan.
Yeah.
Sir, may I request you to give us a 1 minute? So our Dr. Molaya Madam wants to introduce you to the other participants who are living with us from
okay.
current. Yeah, please give us a 1 minute, sir.
Sure, I will wait and let me know. Yeah.
Please do the needful.
Okay, thank you, sir. Sir, already sir has described that sir is a Koenig Endowed Chair Professor at the Department of Electrical and Computer Engineering and the Michigan State University, USA. And just I want to say, Professor Dev's research interests are in evolutionary optimizations and their applications in multi-criterion optimizations, modeling, and machine learning. Sir has received a number of prestigious awards, including Infosys Prize, Bhatnagar Prize in Engineering Sciences, EC Pioneer Awards, GWS Prize in Engineering Sciences, and Bachelor Research Award from Germany, and many more from prestigious organizations. He is fellow of IEEE and ASME. He has published over 550 research papers with Google Scholar citations of over 144,000 with H index of 117. He is in the editorial board on 18 major international journals. Now, may I request you, sir, to kindly deliver your keynote speech to the August gathering. Thank you so much, sir.
Thank you for the nice introduction. Okay, so all these you have mentioned are very relevant today in terms of use of optimization in different kind of problem solving. So one thing I like about this area is that this one doesn't have a boundary. Whether you are in a science department like chemistry, physics, or mathematics, or you are in an engineering discipline, or you are in a business discipline like management science or operations research or any other finance, optimization binds all these different disciplines. There is somewhere you have to use an optimization method. So far in my 30 years of career, I haven't seen any PhD thesis that I have been a part where optimization has not been used. So somehow you end up with a problem where ultimately you have to solve an optimization problem, which actually comes from the core of the problem. So, and that's true not only in academics, even if you go to any industry, for example, any engineering industry for sure, or even HR or other kind of industries, you will see that the softwares that they use on a regular basis has some kind of optimization in them. So today I would like to tell you about the recent developments and a particular optimization methods, which is motivated by evolutionary principles. That's why I decided to put my title as Evolution's Niche for Applied Optimization. So I'll be focusing mostly on applied optimization part of it, but using a special method called evolutionary optimization method. There are various names for that, but I'll go to that one slowly. But I think this conference that you are all attending is very timely and binds all these different methods, that the simulations is a huge part in doing the optimization. So these are some things I think you are going to be talking in this conference. So I'm very happy to participate, and I really wanted to be there physically this time after missing the last December call on another meeting that I was supposed to go. So I guess this is eluding me, but eventually I'll end up getting there. So it's just a matter of time. All right, so getting back to the lecture material of today, as I said, I'm going to be mostly concentrating on applied part of optimization. So you will see some industry applications, and you will see most of the things I talk about is with the applied meaning. So I would like to then first talk about what are different practical problems where optimization is useful, okay, so that you get a broad view of different kinds of problems where optimization is used. And then I'll introduce you to this nature-based optimization that I just alluded to you. And then I'm going to show you why are these methods, which we call evolutionary optimization or evolutionary computing, is so useful, what problems they are very, very much useful. And one of the niche of that is multi-criteria optimization. So I'm going to spend about half of my talk on this particular topic, because this is something that I have been putting most of my time on. And really speaking, most problems in practice, so it really makes sense for us to look at what is multi-criteria optimization and how evolutionary methods can be used for solving such problems. Along the way, as I said, I'm going to give you some examples. One of the things I want to show you, because today's youngsters, particularly a lot of PhD students these days, although they're in engineering, but many of them have a fascination for artificial intelligence and machine learning methods. It doesn't matter what department they are from, they all want to do some work. So we here have started some work in a group that we call DNN group, Deep Neural Network Group. So I want to introduce you to at least a couple of problems that we are working on, and evolutionary computing as an optimization method becomes very useful in such problems. And the last thing I'm going to talk about is a knowledge discovery. Sometimes we do optimize a problem and find the optimal solutions, but sometimes we are interested in not just optimizing, but trying to learn some knowledge about how to solve that problem. So this goes very deep into the philosophy of why we are solving problems. So knowledge discovery becomes a very important part. So I'd like to highlight a way of getting knowledge discovered for a problem using optimization methods. Okay, so let's get started. So optimization is everywhere. So look at this particular slide. It's very busy. There are a lot of different application domains. So first thing I'd like to talk about is on the top right corner here, which is design and manufacturing. So anything you're designing, whether it's an automobile component or whether it's an aircraft component or some other thing, it involves some parameters, as you see, what will be the angle here, what would be the dimension, what kind of curvature, shapes, thickness, material. All these you need to choose before you have a good design, because anything you change anywhere in this, any dimension, parameter, material, you have a slightly different design. So then the question comes, which design is really optimal? So then you ask, what do you mean by optimal? So that means there has to be some kind of an objective function, at least one objective function that will say optimal with respect to minimizing, let's say, the weight of the whole structure here, or optimum with respect to, let's say, maximizing the safety or minimizing the deflection. So there are so many different ways you can prescribe your optimization problem. If you choose any one of them, then it becomes a single objective optimization. If you choose multiple of them simultaneously, then it becomes a multi-objective optimization. One other thing that goes into optimizing are a set of constraints that would say that this overall size is restricted to minimum this to maximum that, okay? The deflection at certain point should not be more than certain value, even after there's a collision, right? So there are all kinds of constraints that can come in. You have to consider all those constraints and come up with a design or a solution that satisfies all the constraints and minimizes or maximizes one or more objectives. So that becomes the whole optimization task. If you want to arrive at an optimal solution, it's not that you just do some calculation and you get a solution. You need to use a computer with a computer algorithm, and that algorithm will start with an initial solution, and then it's going to modify that solution, and eventually with iterations arrives at a good solution. So that's one of the techniques we call point-based methods. But this whole task of doing that is called an optimization problem solving, right? So design and manufacturing, you can see them coming from various different problems. Then let's look at other kinds of problems where you're doing a scientific experiments, which could be very, very expensive to do one experiment. You have done 20 of them. You want to do now 2 more. So you want to decide how to set up your experiments, because every experiment is expensive and time consuming maybe. So you don't want to just randomly do it, but use an optimization method to tell you what would be your next 2 design of experiments. So this becomes very important in industries as well, and also in scientific research. The third kind of problem, which I think goes into the heart of this conference, is modeling. So this is a blast furnace. We want to model the blast furnace, let's say. So steel, you know, that steel is being produced in industry for more than 100 years now. 1905 is when it was started. So there are a lot of inputs that get into this blast furnace, and there is a long-term process. A lot of reactions goes on, and eventually you get molten iron. Then you do some more stuff onto it, and you get steel. So your goal is to get a very good quality steel, no matter whatever are the inputs you are providing here, right? So to do that, first thing you need to know is, how is my output dependent on the input? So this whole process, the chemical process that goes in, which takes few hours, you need to understand each and every time what's happening, what kind of reaction is going on, and all that, okay? Even after 100 years of steel making, you talk to a metallurgist, they could not tell you exactly what goes on. They have a pretty good idea, layer-wise, what's happening, but they don't know exactly what's going on. So there's still some uncertainties that happens in that output to input mapping. So getting the output to input mapping, how is the output dependent on input, is a modeling problem, which optimization can be used to find that. Then the other kinds of problems are inverse problems. These days, tomography, for example, is one where you know the output, you want to know what caused it, what caused the output. So one other way to put at it, if I take MRIs, and I can have lots of 2-dimensional images of my brain, and then I take these images and I want to construct my brain as a 3D object. So how do I do this? So it'll be a computer algorithm that I have to look at the pixels, their color, their positions, and all that. And I need some kind of problem information that how a brain looks like and how the connectivities are from one part to the other part. And that kind of problem information can come in, and you can then construct the 3D image. In terms of engineering, there may be a crack inside a plate, and without cut open it, by doing some kind of waves passing from one point to the other point, you want to figure out if there is a crack inside. So these are called non-destructive testing. Optimization is one way to do this inverse problem solving. Then comes the optimal control problem. Of course, the optimization word is always associated with control. So how do you do those optimal control problem by using optimization methods is a big problem. Prediction is another optimization problem where you take past data and you try to model whatever you're trying to predict. It could be weather, it could be the financial market, or it could be some system which is time dependent. Once you do that, make the model, then you will be able to predict well. So this is a way you can make the optimization research in a more lucrative, so particularly if you're interested in modeling or predicting the markets. Then data mining. Data comes from various different areas. First thing you need to do is cluster the data. Data from one place and another data from another place, are they belong to the same class or they belong to different class? And then clustering of data. So then feature selection, and all these becomes today's machine learning problems, and inherently they are optimization problems. In the middle, I put here an operations research problem, which is usually done by the business schools and industrial engineering people. They do a lot of supply chain. Any product that you do has to have a lot of components coming from different places. They have to come in a very timely manner and in a way that is supportive to the whole system. So you need to plan all that before you have a product coming out with the required demand, meeting the required demand and all that. And then, of course, the placement, which becomes more of a combinatorial optimization problem, where in a printed circuit board, you know that different things needs to be placed, and some of them are connected directly, some of them are not. So in order to minimize the overall wearing, how do you place them? That becomes so that the whole area needed is minimum. So that's another kind of combinatorial problem. There are other combinatorial problems like traveling salesperson and all that. And then finally, the word optimization and the word intelligence has, really synonymous in certain sense. So if you want to create an intelligent system, optimization can be one way to arrive at that, because if you choose your constraints and your objective functions properly, if you optimize those functions, you may come up with solutions that has a built-in intelligence. So many systems like robots and many other systems have been designed intelligently by solving a respective optimization problem. So if you see some of these problems that I talked about, and I'm sure all of you sitting there, I probably touched through some of the interests that you may have in your research. So that means you should be interested in optimization. There's one other problem that I left out, but I put it on a separate slide because this is becoming a very important problem in today's world, simply because our society works in a hierarchical manner. I call it hierarchical optimization. This is fairly recent. I would say about 10 years old. Good algorithms are now being suggested. So if any of you are looking for ideas and areas to get into in optimization, this would be the one where there's not much studies have been done. So let me explain what I mean. So here I'm showing you maybe a government policymakers. Okay, so they work at a higher level, at an upper level. They make a lot of policies like, okay, what should be the tax for a particular fertilizer which has certain amount of nitrogen and phosphorus in them, and then what would be the tax set of fertilizers, and so on and so forth. Why do they do that? Because sometimes these ingredients, they are good for the crop growth, but they are harmful for the society and for the environment, because those nitrogen and phosphorus through water gets into the stream and to the river, and then it pollutes and all that, pollutes the environment. So on one hand, you want to put them so that you get much more crop growth, but the other hand, this is harmful to the environment. So we need to make a balance between the two. Now, one way to do this is government come and says, hey, no farmer can use these kind of fertilizers. But then if they do too much of that, they are actually causing a lot of issues that the farmers come and say, oh, government is our enemy and they are not allowing us to use this and that. So you see, I don't have enough productivity. What government can do is not directly get into what the farmer should choose, but they put some kind of taxation policies. Farmers should take that and then decide which kind of fertilizer should be good for them, because they have to then pay tax on it accordingly, right? So there are two levels of groups here, and each of them have their own objective functions. Government may be optimizing their revenue and optimizing the environmental issues, and the farmer may be optimizing their profitability in order to decide on that. So it's a connected system, but each are not directly kind of telling what the other should do. So when I have a society like that, we should also pose our optimization problems accordingly so that two optimization problems are get connected. So we see that again and again in various problems. I would like to highlight some of it towards the end. Okay, so with all these problems being in front of us, if you try to take any sample of these problems and look at what kind of objective functions and constraints are we talking about as a functions of the variables, you will hopefully see that they are non-differentiable. Okay, they're not continuous. They are discrete in search space because you cannot have any arbitrary value as a variable. Maybe only integers are allowed. I will show you one such problem soon, that there are only integers allowed. So when you have such kind of practicalities, then solving your optimization problem becomes an extremely difficult problem. To make matter worse, what happens is that you often have mixed nature of these variables. Some variables are discrete, some can be continuous, and some can be in a permutation way, right? So that makes everything very, very difficult. Then the large dimensionality. There could be very large number of variables. Today, you will witness an example problem that we recently solved, a problem from industry actually, which we extended, where we have considered a billion variable optimization problem, billion with the B, okay? So 10 to the power 9 variables. Nobody has solved such a big problem yet. So what I want to show you is there could be problems of that size in practice. And I may have an algorithm that I've developed in an academic environment which can only solve 2, 3, 4, 5 variables and doesn't extend it to solve that large variable, then you are not doing applied optimization. So, so we need to sometimes consider a very large scale problem in terms of the variables. There could be very large number of constraints, large number of objectives. Now, in terms of objectives, going from one objective to two objective is already there is a paradigm shift. And then 2 to 3 to 4, it's exponentially gets harder and harder. But as I said, I'm going to put quite a bit of time on the multi-objective optimization. Then nonlinearity in constraints, multimodality, these are all kinds of issues that often come from practical problems. Multi-objectivity is what I'm going to talk about today more. Somebody was talking about uncertainty in variables. So that's a commonplace in applied problem, that your optimization algorithm told you that 50 mm should be the diameter for optimal weight, for example. Now you go and try to manufacture it using any manufacturing process, you're never going to get 50 mm. There is always a tolerancing that every system has. So now if you get 50.1 mm, is your solution even feasible? Or it's too heavy that something else breaks down? So then in that case, if you cannot adhere to the optimal solution, your solution is not of much use. So then you should consider what is allowed. If you say 50, how much you might get, and use that while you are optimizing so that your optimization produces a much more robust or a more reliable solution. So these are some things we always take into account while you are solving practical problems. But one of the major difficulties in solving practical problems or applied problems is the computational expensiveness. We have solved some problems with a Ford Motor Company here, where one solution evaluation takes 2 full days using 500 different computers. So you can imagine how expensive these whole process is. So even if you ask them that, oh, I need at least 100 solutions to be evaluated before I do any optimization, you're easily talking about 200 days, right? So almost a year to solve a problem, no industry will give you that much time. So then how are you going to attack such problems where there is computational expensiveness? So these are practicalities that are not in any textbooks that you will find, but as soon as you go outside the academic domain and try to solve practical problems, you have to face all these things. And of course, the multidisciplinarity, a design or a particular problem may have to be looked at from various different disciplines. Every discipline brings in some variables, some objectives, and some constraints. So you can see that there's a whole gamut of things that we need to consider before we have a good solutions. Let me try to talk to you about the optimization methods now. So far, we talked about problem and their properties. I can classify most algorithms that are existing today into 2 classes, point-based and population-based. Point-based starts with a point. Point means one particular solution. I'm showing you here with the vector x. Then all the algorithm needs is a transition rule. So you apply that rule to the x to get a new solution y, compare y with x, if y is better, then you replace x with y, and then apply a termination criteria on y to see if it's a good enough solution for you to quit. If not, you then go ahead and call x equal to y and then move into that loop. So it's a very simple-minded hill climbing, not much memory is needed. But this kinds of algorithm is very, very sensitive to where you start, particularly in problems where you have multiple local optima, in this case, local maxima. If you start from here with iterations, you can get stuck here. If you start from there, you can stuck here. Only when you start around the global maxima, you may get there. But the problem is you don't know where the global maxima is, right? So there are certain good aspects. They're easy to understand, easy to do a lot of theory because there's only one point to track, but not much of global perspective that you can provide. They're usually not very easy to modify because how do you transition from one point to the other? This t function is usually given. They are often using the derivatives of the objective functions and constraints, and there is not much as an optimization researcher you could do there. There, on the other hand, there are population-based approaches. Instead of a point, you now have a set of points. I call this as P of X. You still have a transition rule where you apply the transition rule to the population to get a new population Q. Okay, and now you take the Q and P together and decide which one would survive. Some from P and maybe some from Q based on the objective function and constraints. And that is checked with the termination criteria. If not terminated, go into the loop. So basically, you start with a set of points, and you move to another set of points and another set of points. This kinds of algorithm requires memory because you're dealing with a number of points. They have a more global perspective in their search. There's a lot of parallel processing. If you have parallel computers, you can use them really, really efficiently, but not easy to do theory because which one are you going to track? There are many points to track here, but they're very flexible to be modified because they don't require gradients or other information. You can say, okay, I'm going to compare this one with that one and decide which one is better, for example. Or you can come and put your own method because you are not using any given procedure. You could just apply based on the problem information. So they are flexible to be modified. Okay, now before I go further, I need to talk to you about this no free lunch theorem, which is called NFL theorem in short. This was proposed in 1997, long time ago, by Olpert and McCurdy. What it says is if you have two algorithms, A1 and A2, and you are trying to say which one is better, A1 could be the algorithm that you had developed in your PhD thesis or many years of research. A2 could be something that is available off the shelf, okay? So you're trying to say your algorithm is better than A2. And to prove that, what you're deciding is that you take all possible problems, all optimization problems that anybody can ever be interested in solving. And you say, I'm going to take A1 and apply to each member of that. Each one will have a performance that how A1 is doing on it. I combine all the performance and come up with one aggregate performance measure called P1. I do the same thing with A2 to each of them, only I make sure that if I have used a particular computer for A1, I use the same computer for A2, same number of function evaluations. And I get performance measures, and I do an aggregate performance measure, and I get P2. They made a long proof which said P1 is equal to P2. So that actually says that if you are interested in deciding whether algorithm A1 is better than A2 on all possible problems, neither one of them is better. So they are equal. That means if your algorithm is doing well on some problems, you know that your algorithm will not do well in some other problems that will exist. So you can never say, I've got an algorithm that is best for all your problems, okay? So these NFL theorem kind of restrict us to make that big claim. And that was published in 97. Since then, all the optimization researchers have been very, very careful in really making a lot of claim. So what it also says, the second part of the paper that says, this NFL theorem breaks down if you are interested in a narrow class of problem. Now you come and say, hey, I've never said I'm interested in all possible problems. I work in the gearbox, in the gear design area. Okay, or in the chemical process plant optimization area. So I'm only interested in different kind of chemical process optimization. Then you can find one algorithm that may be best compared to other methods. So it breaks down. So this theorem, what it tells us is before you claim anything in your paper or in your work, you first say the scope. What kind of problems that your algorithm is good at. What that also says is that if you're today going to solve a problem from industry and tomorrow you're going to solve another problem, you better customize your optimization algorithm for different problem classes so that you make the best possible algorithm for a particular problem class. I gave it a name. I called it customized optimization. So you need to, when you're interested in applied problem solving, you need to always customize the algorithm for the problem, okay? And I will demonstrate that pretty soon. So evolutionary algorithm is motivated by the evolutionary principles of nature, which Darwin's survival of the fittest concept. And we see lots of natural design in front of us, which are really, really optimal in their own purposes and domain. And if you look at how nature has able to come up with such very good design, you see that there are a lot of trial and error. Good solutions survive, the bad solutions die, good solutions have more chances to replicate, and so on and so forth. Only problem with those methods is they have taken millions of years before they become anything useful. We don't have that much time really to solve each and every problem. So we can take the essence from the natural evolutionary principle, put into a computer algorithm, and speed it up so that in a reasonable amount of time, we mimic the principles of nature and get optimization problem solved. So here is such a computer program where you first decide on a solution representation of your problem, whether it will be real parameter, whether it will be Boolean variables or a mixed or whatever. And then you start with the iteration counter, start with a set of points, maybe this set of points you start with, and then evaluate each of them, decides whether you have to terminate. If not, you take this population, select the good ones. So that's where the Darwin's survival of the fittest concept comes in. We call this a mating pool, P dash, which is a subset of PT. And then you use the P dash and apply few genetic operators, like the names are familiar to you, like recombination, mutation, duplication, and all these things we apply. And then we create an offspring population. So maybe these open circles are created from some good solutions from here. So you have an offspring population and you have the parent population, which is PT. We combine them together, apply a survivor operators, meaning what of the parent and what of the offspring are going to survive. And then we increment the counter and go into this loop before we terminate. So if all this works out well, you will see two things happening. Some kind of a representative points with iteration approaches the optimum, and the variance of the initial population reduces as you go down. So these are the two things that happens usually. Because of interest of time, I'm not going to be talking about all the things here that I have, but just to give you an idea of the way the genetic algorithm, which is one of the evolutionary optimization methods that follow that flowchart I just showed you, was proposed by John Holland way back in 1962 when all these have started. So, of course, Holland was not interested in solving such engineering problem. He was a computer scientist. But if I take his idea and try to show you with an example of a can design, where there's a diameter and there is a height, these are two variables, and I'm trying to minimize the overall cost of making a can with a certain volume inside, okay? I can represent my diameter and height in Boolean, in binary strings, which will decode to the diameter and height. And I can put some kind of a number that says what is the objective function, what would it cost to make that 8 centimeter and 10 centimeter of diameter and height. So first thing you do is create a set of random populations. That means you create these strings at random, which will map to these integer numbers. So you basically have these numbers, integer numbers, randomly created. And I'm showing you here 6 solutions that I've randomly created. These 4 of them has 300 milliliter volume constraint inside, so they are feasible. These 2 do not have 300 milliliters, so they violate the constraint. So I'm adding a penalty to say that these solutions are not acceptable to me. And this penalty is proportional to how much constraint is violated. How much is it away from 300? So the actual cost of this one is 41, for this one 49. This is the best one having 23. And this may not be the minimum. Minimum may be somewhere around 15 or 14, which I have to still to go, but this is where I'm starting from. First thing you do is select the good ones from this. So here is a tournament selection operator, which I'm not showing you here, but you can actually pick good ones and make multiple copies like here. And in the process, the bad ones get deleted. Okay, so basically select the good ones from it, make multiple copies of them. And then you pick any 2 of them and apply a crossover, what you do here is take the two solutions, look at their chromosomal representation here, choose a cross site at random, and swap the right side information between them. So these two parents is crossed over here. So this get attached with that, and I have a new solution. And this gets attached to that, and I get another new solution. So from these two, I get these two as an offspring, right? Like that, you apply them in pair, and you create an offspring population. What you do after you do the crossover here, you take each one of these solutions and suddenly change a 1 to its complement. For example, here, this 0 or this 1 has been changed to a 0, the fourth one here suddenly. And then either you may have an improvement or you may not have an improvement, but this mutation is an insurance policy of your population to get stuck at certain values. So both are important. Together, they work really well, but as a one particular operator, it may not be so well. So here you can see a simulation on a two-variable problem with two constraints. In this left side, the feasible region is here and the optimum is here. And in this case, I changed the sign of the constraint. So the feasible region is here and the optimum moves to this point here. So you can see, starting from the same initial population, how such a simulation with time, with iterations, first locate where is the good region in both situations, and then it kind of creeps towards it. Like here, from near here on, it's actually creeping. So you can see that this kind of method has a global perspective in the beginning, where it can tell you where to go. And soon after that, you can leave this kind of algorithm and use a point-based method. So a best hybrid method is starting with a population-based, ending up with a point-based would be a very good algorithm. Okay, not only two-variable problem. I start with two variable. As I said, I'm going to take you to a billion variable journey soon. But there are many practical problems that are solved using these evolutionary genetic algorithms. This is the Mitsubishi Regional Rate 2000 Jet 2017. Everything you see about the plane, the internal seating, all the arrangements, these kinds of shapes and everything was designed using an evolutionary method. This is Japan Shinkansen, the bullet train. The nose of it was designed using genetic algorithm because the point-based methods has failed. It couldn't find a feasible solution. This is Kone's elevator system in a multi-story building. People are pressing the button at various floors. Every half a second, there's a controller, and I can show you, I've taken it from the manual. The controller allocates the landing calls. That means which car is going to stop at what floor is decided by a genetic algorithm. And this is in operation since 1995, not just recently, but many, many years ago. So there have been, these are just few examples I'm showing you. There are a lot, many more now these days. Almost regularly, people are using in industry. Okay, these kinds of methods are very, very flexible. Because they are population, you can use them in various different ways. If you're interested in finding the global optimum, they are good candidates. I'm not saying there is a proof that this can always give you the global optima. By the way, no algorithm, including classical point-based methods with derivative-based methods, has a convergence proof for any arbitrary optimization problem. If it's convex, linear, quadratic, yes, there are provable algorithms. And in those cases, you should not use these kind of population-based approaches. You should use those provable methods. But most problems in practice do not provide a proof for any algorithm. So you are as good as any other algorithm, then these methods provide a much better global perspective. But they are also potential to be used to find multiple solutions. And this is where the multi-objective optimization comes very handy. Okay, I don't want to talk about these theoretical aspects now, but these are direct approaches because we don't need any gradient. They are excellent in handling procedural objective and constraint function, like if something happens, do this, otherwise do that. That kind of description of objective function and constraints are excellent to be handled. Okay, these methods are good for concept development as well, like for a robot, for example, to navigate where the robot hasn't seen on all the obstacles beforehand, but you want to come up with. So it's a more generic concept solution you want to come up with. These are excellent ideas. Parallel implementation and hybrid implementation, as I said, of course, makes a big impact in this kind of using this kind of algorithms. Now, I mentioned to you about customization. So I need to talk about what I mean by that. Let's say I've got a problem where I have this knowledge. So it's obviously some problem knowledge has to be utilized to make an algorithm customized. Say the first variable has to be always bigger than equal to the second variable, bigger than equal to third variable. So there is a monotonic reduction in the value of the variables. What kind of problem are we talking about? Well, you think of a cantilever beam. Those of you who are in mechanical or civil or structural engineering, you know that if it's a cantilever beam, you apply the end load, your optimal design will somewhat look like that this has to be heavy. And then as you go towards the end, you can reduce the dimension. Okay, so here, if this is your X1, that's your X2, you will have such a scenario. Or you're designing a building, multi-story building. The ground floor will always have maximum dimensions. As you go up and up, your dimensions can reduce or become equal to the previous one. So there are many such situations where, as an engineer, we know that we are expecting this. This is not to say that I've already told you what is X1, X2. I'm just saying their relationships are like this, that X1 has to be bigger than X2. Now, if you have that problem knowledge, which you have acquired by doing an undergraduate and 30 years of experience in the industry, and you don't want to just say, no, I don't know anything about the problem and I want to treat it like a black box, right? Now, if you have that information, how can I help an algorithm? Well, instead of using X1, X2, X3 to Xn, I say X1 is my variable. Instead of X2, I'm going to use a new variable I call P2. And P2 is X2 divided by X1. Okay, so it's the ratio between X2 and X1. That's my P2. That's my variable. And this variable I am restricting to lie between 0 and 1. Because the upper bound of P2 is 1, X2 can never be bigger than X1, right? So by forcing P2 to be replacing variable X2, I have forced these conditions to be satisfied. You can see a heaven and hell of a difference with the same optimization algorithm if you use these kinds of variable setting vis-a-vis that kind of variable setting. So these are the customization. You are not solving now any arbitrary problem. You are solving this problem which has certain properties, and you have now customized an algorithm using either coding or using some kind of new crossover operator or a new mutation operator to do that. There are many, many other things that we have done, taking the advantage of the knowledge that the problems give us. Now, let me show you this example, which one is a billion variable on that I just mentioned to you. So this one came from PTC Industries. So it's a foundry, problem from a foundry where you melt a certain amount of metal, and then you have to pour the metal to make some castings. So the particular vessel we are working with was having 650 kg of metal melted. And then there are lots of castings you could do. So let's say you have poured it to few of them and 10 kg are left. And that 10 kg you cannot pour to anyone because nothing is less than 10 kg. So that becomes a waste. So then if you come and say, oh, if I have done some other way, maybe 5 kgs would have left. So I would have saved some energy, right? So the whole problem here is if you do one time this task, then you don't have to do any algorithm. You could just manually do it. But this company was doing for the whole month, and they had to do it many, 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 many times. And then doing it by hand was a difficulty. So the person who came to me actually wrote an Excel code, and he would run it after his dinner before he goes to bed. And next day morning, he gets up and looks at the solution. So it takes the whole night, and he gets about 70 to 75% metal utilization. And he could see certain places he could actually do some manual change and it will still improve. So he was not very happy with his code. He came to me and said, maybe you can help me with this. So first what I did is I formulated the problem. And it turns out that it's a maximization problem of utilizing metal. Xij is my variable. And it turns out it's a linear function. Then I have some constraints that comes with the problem, and they're also linear. So it's a linear programming problem. The only difficulty is that the Xij has to be non-negative, and it has to be an integer. So I told you that certain problems may have only integers as their variable. Why are they integer? Because Xij talks about how many copies of a particular casting you want to make from a particular heat. You cannot make 2.3 copies. That means that you make 2 copies of this casting and 30% of the next one. You can't do that. And then 4 hours later, you come back and put the rest 70%. You can't do that. You have to either do completely or not. That means your variable should be an integer or 0. It cannot be negative as well. Now, believe me, this particular restriction that xij has to be an integer makes all difficulties in the optimization algorithm. So if you don't have that, it's a linear programming problem. You could use Karmarkar's method. You could use other methods of linear programming, and you can solve millions of variables. Not a big problem. But this causes them to use a branch and bound method, which is that comes in, and when you have more and more variables, the branching becomes more and more. Although there are some good softwares that are available, like Ciplex and GLPK, Guravi, but they all have their issues. So let me show you on a small version of this problem, which requires only 310 variables. Ciplex does it. Ciplex does it well, okay? But GLPK cannot solve it. Then if we go to 1,000 variable problem, so I increase the number of copies of these castings that I have to make to increase the number of variables. Ciplex still does it in 0.13 seconds, and you get 99.462% metal utilization. But when I go to 2,000, it doesn't work. So from 1,000 to 2,000, somewhere in between, it stops working. And I did some more study. It turns out it's 1,800 where it works, but beyond 1,800, it doesn't work. There is no magical number here. It's just that the problem is such that beyond 1,800, there are too many dimensions. And you may have heard optimization algorithms are cursed with dimensionality. Okay, so it's called curse of dimensionality. It always happens if your algorithm is not scalable. So I actually contacted the Ciplex people, and then they also found very similar results, 2,000 variable problem they cannot solve, and they pointed me the culprit, which is this branch and bound method, which I suspected, but I never got a solution from them. They helped me solve the 2,000 variable problem, but then they said, you probably not be able to extend with that idea some more. But here for this industry, we had to use 50,000 variables. So we are stuck at 2,000. We have to give them a 50,000 solution. So we developed a customized evolutionary algorithm for solving that. We use some initialization, which is problem specific. And then I use a recombination operator, which is very interesting. So let's say I'm showing you a partial solution, only the 4 hits here for parent 1 and parent 2. So these are 2 population members. The way I create my child is this. I look at the first assignment. So this basically says that from the first hit, create 1 copy of the second casting, 1 copy of that casting, 1 copy of that casting, and you'll be utilizing 343 kilos out of 650 kilos. This solution says, make 1 copy of the first casting, 1 copy of the third, 2 copies of the fourth, and 2 copies of the fifth, and 1 copy of that, and 3 copies of that. You will be consuming 625. You still have 25 kg left in the vessel, right? So now I look at this solution and that solution. Which one is better? Obviously, that is better because I am able to utilize better. So I take a copy of that and put into my child. Then I look at the second one and second one. I notice that, oh, this one has over specified because it required 808 kilo. This one requires 667, slightly more than 650, but this was a bit close to being feasible than that. So this is still better. I take a copy of that and put into my child. Then I go to the third one. This one 629, this one 606. That's definitely better. So I take that and I put it here. So like that, I take some from here and some from there based on how well they're doing, and I create my child. When I do that, there are a couple of constraints I had. One is that their sum has to be the demand. Their sum has to be the demand. Both these solutions meet the demand, but the way I fabricated it, now I'm not satisfying that demand. So first thing I do is I create a mutation operator to fix it. Adjust this number so that I meet these demands, okay? So that made my solution feasible in terms of one type of constraints. And the second mutation comes in trying to make these inequality constraints satisfied, that the overall weight that I need to make them should be less than equal to the vessel size. Sometimes I'm able to do that. Sometimes I'm not able to satisfy that constraints. But the first, these demand constraints, I guarantee to be satisfied at every time. So we do that, and I put this into an algorithm. you can see that I can solve all those small size problems, same accuracy with a much smaller time. Okay, even 2000 variable, now I can solve in 0.19 second. But from now on, I'm going to show you everything on a 1 million version of the problem, because 50,000 was a piece of cake, which the company needed. It just gets solved in 10 seconds. But I'm showing you on a very large scale version of the problem that recombination is an absolutely essential thing. Without recombination, you will not be able to solve this problem. So first things we do is see which operator is more important and which operator is not so important. But here's the big picture. You can see the x-axis. I started with 50,000 variables, which the company needed. And as I said, I solve it in less than 10 seconds. Then I increased to 100 to 500,000 to 1 million to 5 million to 10 million, all the way up to 1 billion, right? So that company at this today do not need this. So this is more of an academic exercise. If anytime anybody needs such a big problem, we have an algorithm that can solve it. And you can see how nicely these problems are solved with a polynomial time performance on a very large range of problems. As I said, no optimization algorithm has shown yet to solve such a large scale problem. And the problem got motivated from practice, but this part of the problem is currently company do not need. But sometimes industry think that, oh, I have a 1 million variable version of a problem. Can you solve it? So I can go to them and saying, you see, we've gone even 1,000 times more on a different problem. So maybe we can have a look at that, because then you start to build trust, rather than if you say, all I have solved so far in my career is only up to 10 variable problem. So 1 million, I'm not sure. And you don't really come up with a very good impression when that happens. Downsizing is good, but upsizing is never good. So the problem is still difficult to solve. But if what I'm trying to say is, if you are interested in an approximate solution to the optima, then you can find the polynomial time algorithm for such problems. Okay, I thought I'm going to spend half the time on multi-criteria, but it'll be less than half the time now. But let me try to make a justice to this multi-objective optimization now. So far, I gave you an idea of why optimization we should be paying attention to, because they come in most different problem solving. I showed you the difference between point-based and population-based, and one example where you can see that such a population-based algorithm can be scaled up to solving such a big problem. Okay, now multi-objective optimization, which you often face in practice. A simple example is, if you want to buy a car, first thing you look at is the cost. How much is going to be that you have to pay from your pocket, right? If that's the only objective you are interested in, you all will be driving the same car, same looking car, right? But obviously there is some other thing we are interested. It could be the comfort, it could be the safety, or some other objective that is in conflict to this first objective of cost. Now, if you go and say, what would be the best solution for a comfort? Maybe you are looking such a car, which can be 10 times more expensive or 100 times more expensive, right? So if both the objectives are of importance to you now, the question is, are these two the only optimum? And the answer is no. There exist lots of other solutions, which I'm showing you here on that red line. Falling there, these solutions becomes Pareto. Optimal. Pareto is the Italian scientist who first proposed this idea. So you still have an objective space where if somebody is not using an optimization method and trying to solve this problem, they will probably end up in this blue region. Here is one such example. But if somebody is using an optimization method, they will always fall on this red line. So if you find this point A, then A is better than this in both objectives. It's cheaper than that. It's also has a higher comfort than that. So if both these are of interest, A is an optimal solution compared to that. So now if I'm doing optimization research, instead of finding points here, I should be finding points on this red line. Now the question is, shall I find A, or shall I find B, or shall I find C? So it so happens that in these kinds of problem, when you go from one objective to more than one objectives, there is an optimization task where you go and find these points. The other is a decision-making task, which means which one I should pick from here. Unfortunately, the decision-making depends on where in this Pareto front your point lies. So it's a good idea to find a representative set first and then make a decision. Okay, so optimization followed up with decision-making. There are, of course, classical point-based methods where you can do a weighted sum, but people have shown again and again that weighted sum solutions do not work if you have a problem with a non-convex Pareto optimal front. Like with the weighted sum, you can never get a point between B and C. All you can get is A to B and C to D, no matter what weight you choose. There is a theoretical proof. So this is not the very good method if you want to use a point-based single objective optimization. There are other methods there which has certain other difficulties as well. So back in early 90s, when I just moved into IIT Kanpur, first time we proposed this idea of evolutionary multi-objective optimization method, where we take the problem and devise an algorithm to find a nicely distributed set of Pareto solutions. Once they are found, then you can make a decision and pick one from it. So that was the idea. But more and more people have found there is a diagonal path that decision-making and optimization can be put as we are going from one iteration to the next is a much better strategy. So I proposed this concept called NSGA2, which is the elitist non-dominated sorting GA. Again, because of time, I'm not going to go into, but it's a very celebrated paper. You'll find this on the internet. So far, it has about 36,500 Google Colors citation, just one paper. I will show you rather its technical working principles, rather how it works. Here is a simulation on the left side. It can do 2 objective and 3 objective very well. So here, if you say there is a 2 objective problem, starting with this random set of points, you can see how the points can come and converge to this Pareto optimal set. So when you're minimizing both objectives, your red line comes over here. There's nothing below it. So all you could do is represent this whole Pareto set into 10, 20, 100 different solutions, depending on as many you want. So this algorithm works very well for such cases. Recently, we proposed NSGA3 because these kinds of methods do not work when you have more than 3 objectives very well. So then we developed this NSGA3 approach, where when it comes around, you will see that the point starts from here, and we have to guide this kind of search with all these arrows that are flowing out from the origin. These points get cling to one of these arrows and go all the way down to the Pareto. And you can see how nicely distributed 3-dimensional problem you can solve. So there are F1, F2, and F3 need to minimize, and you now get a Pareto surface rather than a Pareto line. So we have algorithms now which can go from 1 objective all the way to about 15 to 20 objective problems. We noticed recently when you go beyond 20 objectives, which no industries have come to us yet, but we want to be ahead of that. So we started to work on what I call is the evolutionary massive optimization involving more than 20 objectives. But with NSGA3, you can see we can solve a 10 objective problem. This is called a PCP plot, parallel coordinate plots. If you want to find only in the middle, you can find. If you want to find with few points, if you want to find a practical problem, this is a car crash worthiness problem, and you can see you can find these red dots are the NSGA3 points, constraint problems, and all that. So this is the codes are available in Python from GitHub. We call it PyMoo, P-Y-M-O-O. This is public domain, so you can download and use them. The codes are in Python. We also have MATLAB codes now, and also C++ codes on our website. With all this development, the decision-making became an important part, and people started to figure out how to do decision-making. Like I said, a diagonal approach. So one thing you can say beforehand, I'm not interested in the entire Pareto front, but I'm only interested in certain parts of the Pareto front. Now, you obviously don't know this Pareto line, so you represent some points called aspiration point beforehand. So if this is your complexity, let's say you're trying to solve a machine learning problem where you have 2 objectives, you want to minimize the error and minimize the complexity. So you say that, well, I have to have a very small error, but I can go for a large complexity, or very small complexity, but I can tolerate a little more error. So these kinds of aspiration points you can provide before you start your optimization. And these kinds of methods, which we call reference point-based NSGA2 or multi-objective algorithm, can find and give you the points which are close to these reference points that you supplied, not the entire set. So this way you are faster, and you are giving your user the solutions that they're interested in. There are various ways of doing these things, of course. Then comes the a posteriori decision makings. Once you find a set of points, how do you choose one? There are various ways. One is called the compromise programming, where you go and find the nearest point to the ideal point and get a solution chosen. Or you can do a trade-off analysis. Most recently, we've been doing these kinds of analysis of trade-off. That means going from one point to the next, you will sacrifice on some objective, but improve on certain other objectives. So you then do that ratio of sacrifice by the improvement and find out which point is more worth. So sometimes it's called surrogate worth as well. Then there are concepts. So these are particular decision-making approaches that after you find a set of points, you can use those decision-making concepts to pick one solution. Okay, now getting to some applications to machine learning. So this is the one I wanted to show you, that here we started work in the deep neural architecture search, where there are lots of images that are available. There are different kind of data sets. I'm showing you a few examples here from the ImageNet data set. So these are images that are available. Some of them are with the pandas, for example, and some are with burgers, and some are with some other thing, different shapes, maybe domes, cats, dogs, aeroplanes, all kinds of stuff. And each one of them may have 1,000 different images, okay? Now you need a system that will take the image as the pixel, RGB value, and then you should be able to say whether it's a panda or it's a burger or it's a cat or a dog or whatever, okay? And you want to do this with maybe 98, 97% accuracy, okay? It's not an easy task. So we have come up with a neural architecture search along with the weight learning using a multi-objective concept where we do this error minimization and complexity minimization, like I said, because we could do a much better search if you use two objectives in the search process. And we are now the state of the art. Here you can see our Pareto fronts, and there are different solutions. They have each all fall over here. So if you're trying to have a minimum complexity and maximum accuracy, okay, if you're on this corner, you are better because you have high accuracy with small size. And you see red points are our points, and all these other ones like Lemonade and Amobab nets and darts and ResNet and all these are over here. So we have outperformed some of these very, very well and expensive algorithms that people have come up with simply because in these industries, they have lots of GPUs that they can use. All these were done in our 8 GPU system. It's because our algorithm is so powerful that it can beat the hardware that other companies are using. This kind of work we've been doing by using multi-objective, our knowledge on the multi-objective optimization to help this machine learning problem. There's another one we recently did where we wanted to do a neural architecture transfer search. So you have, let's say, 50 different problems to solve, but you want to solve maybe 5 of them and use the neural architecture that you've created to solve other problems. So that way you can transfer what you have learned from one problem easily to the other problem. So here there is a whole lot of things I need to talk about, but it's basically, again, becomes an architecture search along with the weight learning. We again use multi-objective. In this case, we use many objectives. You've seen this kind of a plot before when I had 10 objectives, and this is a particular one with 11 objective problem. And we are able to find a solution with the decision-making that I just talked to you about that outperforms if I create one particular solution technology for each one of the data sets. So we've got one algorithm or one neural net that solves all these problems much better than one algorithm specialized for each of these problems. So that's, I think, is the future of how you can use the knowledge of optimization in improving machine learning problem solving. The last topic I'm going to talk about in 3-4 minutes is this concept which I gave it a name a few years ago. I called innovization. Innovization comes from 2 words, innovation and optimization. So what it says is we can learn some knowledge for a problem from the optimal solution. So through an optimization process, we can learn some knowledge. And often those knowledge are innovative knowledge. So that's why it can bring in innovation. So what do I mean by that? So let's say I am solving electric motor. So that's my company, and we just always design electric motors. And we've been doing it for many years for different sizes of motors, each having different rating. What I can do one time is I could maximize the electric power rating and minimize the size of these motors. So with these two objectives, I can find multiple Pareto solutions, right? So that means I've got different optimal solutions for different applications. Now I can look at how the solutions are. That means if I open the box, I will see an armature. I will see the diameter of the armature. That's one of the variables. I can see there is a wearing. So I have the wear diameter, I have the insulation thickness, I have the number of turns I have made. All these are my variables here, and they will be changing. And that's how the shape is, the size is changing. Now, if you ask an engineer, when I go from here to there to there to there, do you see those numbers changing randomly, or do you expect there will be regularity? And the answer is always yes, there's going to be regularity, because you have laid them in a way that increases the rated power. So obviously it will reflect there. Now imagine after I find these things, and if I analyze how these dimensions are changing, how these variables are changing, I can discover some knowledge. I can discover some principles, some thumb rules of how to change the design from one to the other to increase my power, right? And those bring in the innovation that I have been talking to about. So let me show you on a gearbox design problem having 28 variables, 101 nonlinear. So it's a real world applied problem. I found here 100 different Pareto solutions. What I observed, 27 of them are more or less same. They are not changing. Only one of those variables is changing with the Pareto solutions. Okay, and you can see how nicely they are changing. It's a discrete variable. It's called the module. And if I fit a curve through this, it turns out module is in proportion to square root of power. So this is a knowledge I didn't know, but doing the optimization, analyzing it, I found that if I always make my module in proportion to the square root of the power required by these gearbox, then I have designed it optimally. Imagine how powerful and how knowledgeable the user, the designer would be once they discover this kind of innovation. So since these studies, which I first started to notice starting around 2000 when I started to work with industries, this has become now a major area of my research here because of industries around me, which are mostly auto industries and chemical industries. They are really very much interested in doing these kinds of knowledge discovery study. Because human mind, after all, is always inquisitive, and finding solutions, good solution is one thing, but trying to understand why they are good, it always interests us. And I think I accidentally stumbled into this kind of idea of how to do that. So we are getting into this concept of explainable AI, that we do a lot of machine learning, but can we explain them using this innovation concept? So this is, we've been doing this kind of study where the very complex systems like a neural net or a reinforcement learning methods cannot provide you that kind of an insight, but we come up with very simple rules. As you see here, we call nonlinear decision trees, or NLDTs, which can give the variables and comes up with a function in a decision tree manner that can explain how a car should maintain, let's say, a 30-meter of distance from a previous car, although the previous car may be driving crazy, but the control system here will always maintain a 30-meter distance, for example. So, that kind of problem we've been doing a whole lot. Here is another example we did recently, which is much more complex. It's called the lunar lander problem. So this is a spacecraft. There are 8 state variables and 4 action variables, whether to put the left engine on or the right engine on or not do anything, or you just go down. So you can see that with our very simple rules based on these state variables, we are able to come up with and explain how a complex neural network is able to solve such problems. So I think there is a whole lot of research now going on in this particular area. When these machine learning algorithms are getting more and more popular, people are now interested in seeing how are they solving the problem? Can you explain to me how is solving the problem? And I think through this innovation process, we are able to capture that knowledge. So I think there is a whole lot of stuff here that optimization can bring in, not only just finding the solution, but trying to explain what things are happening. I think I need to cut off here, and probably I'll take some questions rather than continuing with this. I had a few more slides here about uncertainty handling and all that, but I'm going to leave it for now. There's another application I had here, but that's okay. So I just want to summarize here saying, I think I already mentioned that classical methods are the point-based methods I talked about. Don't ignore them. They provide you the foundation. I think it's good to start, and somebody mentioned to me about my books. I always start with those simple point-based methods. So they're very good to get first, and then continue to do more complex methods like evolutionary algorithms because they are flexible, they have parallel searchability. Customization is often the key if you want to solve applied problems. And multi-objective optimization is like coming in a big way because it can provide that knowledge that I mentioned to you, and it can solve multiple objectives the way they come in actual practice. So I think it's a very exciting area to be. And this, I'd like to stop, and if time permits, I'd like to take some questions.
Thank you, sir, for your plenary talk. Now we can take 1 or 2 questions from the participants. Participants, please.
Hello.
Any questions from participants?
Good evening, sir. This
Yes.
is
Go ahead.
Listen, you. I would like to say that, sir, when I started my research in.
Yeah.
Hello. So
yeah,
I
can
would
hear
like
you.
to say,
Yeah.
sir, when I started my research in 2008, can you hear me, sir?
Yes, I can hear you. Yeah, go ahead.
Oh. So, sir, I had gone through the multi-objective optimization. I had also gone through your paper, that NSG paper, you Amrit Pratap, and you had published that paper.
Okay. Yes.
So it was since that day, sir, it's a dream come true actually to listen you. I was patiently listening you, and I have noted down few of the points. But I have a query, sir.
Yeah.
Mostly I work on population-based optimization methods, swarm and evolutionary. And most of the practical problems in electrical power systems, I found that the variables are mixed integers and nonlinear problems. And the search spaces are also discrete. In most cases, constraint equations, discretes, and all. But for multi-objective, as you said, that when it is better to start with, no, not in multi-objective, but in other point you have said that it is better to start with a population-based approach in the beginning, and then when the solution is about to convert, it is better to shift to point-based methods.
Point-based.
So
yes.
Yes. Now my question is, in case the problem is a non-convex and having a mixed integer variables associated, and objectives are also discontinuous, and then in that case, whether this point-based method at the last stage of the optimization would be applicable,
useful or not. Yes, that's a very good point. So if only you can apply point-based methods to the problem that you have, then only you switch to the hybrid. But if there doesn't exist a way to apply a point-based methods, because there are different kinds of point-based methods. One is a derivative-based, so which requires that the objective function and constants should have derivatives existing. So if that doesn't exist, you can't use the derivative-based approach. But then there are direct approaches like Nelder and Mead. There are various other methods that are there. So then you can switch to some of those. Or you can simply use a hill climbing, like I mentioned. You just create a random point around your current point using a Gaussian distribution, compare with the parent, and if the child is better, you accept it. So that's how you continue, right? So you can have a very simple algorithm like that. There are other methods like taboo search and all that. So if only you think that I have seen a paper where these kinds of problems are handled with the point-based methods, but they had done some approximations, So I don't want to use that as my main algorithm, but I want to first start with maybe an evolutionary population-based approach. So I end up in a good region. You remember that the very beginning I showed you this point difference between point and population-based. Let me quickly get to that one. Yeah, here. So are you seeing my screen?
Yes, sir.
Okay. So the point-based methods work very well if you are near to the global optima, right? So if you think of using a evolutionary algorithm in the entire search space, and very quickly you can come over here because the evolutionary method have deleted all that because they are not so good, and you are already here. Now you can leave evolutionary method and use a hill climber, and you can get there, right? No, so that means you're right that you need a good hill climber as well, because if that's not good, you should not switch to that one. But what you could do is you can still keep your evolutionary method and start to shrink your population size, because the difference between point and population is in population-based methods, there is a population of points, and in point-based, there is one. So you can start to emulate your population-based more behaving like a point-based if you start to reduce your population size. So you started with, let's say, 50. With generations, you reduce them to maybe 40, 30, 20, eventually stuck to maybe 4. And then just deal with the 4 and you end up with 4, because now you have a more focused search. So as you start with a large population size, you have a more global search. As you reduce the population size, you are behaving more like a point-based. So because point-based has this ability to focus, and the population-based has the ability to make a more global search, right? So starting, you need a global search. At the end, you need a more focused search, although you could keep the global search once in a while going. So it's how to balance these two is really the main issue in optimization. So if I have to solve an industry problem where the time is money, time is the essence, we try to use everything we know in optimization. But when you're trying to publish a paper for a journal, if you try to mix all this up, reviewers will rather not evaluate your paper with a very high value. They would say, oh, you mixed your algorithm. One algorithm doesn't work. So how good is your algorithm? So it's a two different world, academic publication or academic research versus industry or applied research. What I try to concentrate today is more on the applied side. It may not help you much with the academic side, but sometimes you should do meaningful research, like staying so much time in academics. You should propose something that may be useful for applied. But I see a big gap between the two. I've been fortunate to get a lot of industry problems, so I could do both. I'm doing with my students more academic research, and with some students I solve the industry problem. So I could see both, because you can get ideas from both. But unfortunately, this gap needs to be reduced as we go ahead, which means basically more and more journals should be more open to applied algorithms that are more meaningful. There is a reason why you are switching, and this is practically motivated. And then you are showing it on very complex problems like a billion variable or a very complex nonlinear problem, where you show that your hybrid method still works rather than one algorithm from start to finish. So we are getting there. More and more applied journals are coming up. But I think as an academician, we have to take that lead and show and publish algorithms that are more readily applied. Otherwise, industries will never pay attention to what academics are doing. And already there is a lot of apathy for industry people to work with professors because they think we can only solve a very well-defined problem, which is of not importance to them. But yeah, and that's in general true. But I think we need to go and solve more and more practical problems. But these are good questions that you are asking, and I think we need to show them, and we need an opportunity also through journals and books and other pub conferences where we can talk about these practical aspects.
Sir?
Yeah.
We have one question from Yonchak Shu. In nature, the environment changes and the problems to be solved also changes. How can we deal
Dynamic.
with such a case
Yeah.
where the objective function themselves evolve over time?
Yes,
And furthermore,
yes.
is it possible for an agent to actively change its objective function?
Oh, yes. This is another big area of research these days. I see we just concluded two of our annual conferences, and there had been tutorials, there had been special sessions on this topic called dynamic optimization. So there are, and dynamic multi-objective optimization. So there are papers that we have on our websites, you can see, where problems on test problems, which are academic problems, which changes with time as you are optimizing. We have created those problems. So in this kind of situations, optimization can never get to the optima, because by the time you are getting there, the problem has changed. The optima has moved to some other place. So you always have to track the optima. So now the performance of the algorithms are judged based on how close you are able to track. Are you far away from where the optimum is when it's moving, or we are able to come close? So that's how you judge these methods. And there are all kinds of algorithms coming up. And also there is other aspects of it which are online optimization. So the one thing is the problem is changing with the time, and then you are trying to track. And the other aspect is, are my optimization algorithm now ready to be applied online? So for example, in an optimal control problem, let's say I'm dealing with a particular PID controller, for example, but I want to change it with the evolutionary algorithm-based controller. At every time step, I sense my state variables. Now my controller has to tell me what to do, what kind of action to take. And then the next time step, it has to tell me what action to take. So basically, online, I have to optimize like a robot, avoiding obstacles and trying to go and navigate, right? So here I had an example somewhere. So if you think of that, every time step, the robot has to optimize and find out what should be the path it should take. The problem is defined that way, but there is a different way we solve these kinds of problems. We say, we don't want to know what is the current scenario, but we will have a generic problem-solving technique here, where we have created the brain of this particular system, where given the distance of the most critical obstacle to my robot, and at what angle it's coming from me, I have to decide how do I move. If I can come up with this matrix, if I can fix, so A means go ahead, AR means ahead right. So these are fuzzy descriptions of what the robot should do, ahead left. And this is the angle is my critical obstacle is my ahead right of me. And it's very near to me, near, far, and very far to me. So based on these two combinations, I have optimized this particular table and come up with these kind of things. So you do an offline optimization, come up with the brain of this system, and now it can navigate in a real world scenario. So these are also online optimization. So what you mentioned about problem being changing and the optimization being applied online, these are very related. And there is research kind of going on in all these. But frankly, with my many years of working with industry, I haven't yet gotten one problem where the problem changes with time, except one situation in electrical power dispatch problem, where the demand, where this power generator is supplying the power, the demand is changing with time, and that changes everything. So yeah, we've been addressing some such problems, and that's another area of optimization research today.
Sir, we have another question from Suprajit Datta. How can we compare optimization's algorithm?
Different optimization algorithms. Okay.
Yes. What are the dominant performance measure we can consider, like speed, accuracy, and robustness, etc.?
Yeah, that's a good question. So first of all, you need to keep many things fixed for two or more different algorithms. So one of the things we try to keep fixed is the solution evaluation. So how many total new solutions we looked at from start to finish of every algorithm, right? We try to control that. We try to make it fixed among all the methods. And then when that function evaluations have completed, we look at what is the best solution we have found so far. And then we compare the solution quality of each of these methods. And that's how we judge. You could also do the other way. Like you say, I will run each and every algorithm till I get a particular solution quality. And then I see how long did it take? How many function evaluations did one algorithm require? The one requiring less number of evaluations is obviously better. Now, when you get to multi-objective, so let's say there are two multi-objective algorithms you're comparing. So now you don't have one function value, there are more than one. Then there are metrics like hypervolume and inverse generational distance, or IGD. So we actually combine these multiple objectives into one number, and then we can compare those numbers, because now we'll be comparing two sets of solutions rather than one solution from each method. We'll have a sets of solutions from each method. So things gets a bit more complex, but we've been doing this for many years. So we've got some nice statistics-based comparison techniques that are available. So all these methods, evolutionary methods, are stochastic. So you need to run them many times, and then you have to compare their median performances, or there are more like Wilcoxon rank sum tests. There are different kind of tests which are statistical tests that you have to do in order to compare two different stochastic algorithms for their stochastic performances. So yeah, there's a whole lot of, so if you read some good papers on comparison kind of papers where anybody comes up with a new algorithm these days, first thing they have to do is they have to compare with the existing methods. And you will notice there how they do it. There are no one way people are doing it. And unfortunately, many of our journals demand that. And I don't always support that, but many journals demand that you compare with almost all leading existing methods before your algorithm can be published. And that can be very, very tiresome. But unfortunately, that's how the whole, the research is going, and journal seems to be encouraging it. Yeah. So you need to be very good at these kind of comparisons, because you have to do that if you want to publish in good journals.
Sir?
Yeah.
We'll take two questions, if you permit, sir.
No, go ahead.
Okay. We're having one questions from Dr. Anupam Biswas. In evolutionary DNN, whether weight learning or neural network architecture or both are better?
Yeah. Yes. We do both. So, but it's a bi-level problem, which I started to talk about. So if you take this one, for example, so we have a neural architecture like this, and inside this, there is a network. So this architecture we are searching, and inside this, the network also we are searching, right? So the whole architecture is searched. But if you go to the neural network in each of them, there are connection weights. So there is another kind of learning there, the weight learning. So one thing is the topology learning of the whole architecture. The other is the weight learning, which is inside, right? And that's how you get into this hierarchical optimization that I talked to you about. Here, the upper level is the architecture. And we get the laser pointer. The upper level is the architecture. The lower level is the weight. So in most of our studies, we use the backpropagation, and there are stochastic gradient learning methods for those that are available with PyTorch and other methods. So we use them straight away. We don't invent there anything new, because those are very, very efficient. So we use the weight learning, not evolutionary method, but using the standard error minimization with stochastic gradient learning. But the architecture search we do with the evolutionary method, because that doesn't have a gradient, and it's very difficult to use any point-based methods to search. And in fact, what we use there is a multi-objective, is NSGA2 algorithm. We called it NSGA-NET method. So where we have two objectives, one is the minimizing the error and minimizing the complexity, or the minimizing the number of weights that we have, or number of parameters that we have over here. So yes, you are right. There are two kinds of variables, but they come in a hierarchical way. And we try to treat them as a bi-level optimization, which I introduced a little bit in the beginning with the government and farmer, a very similar thing, the architecture and the weight. So you can look into our papers. So if you go to our website, which I showed you here at the end, maybe I put that up again. So you can go to either one of these. This is my personal website, and this is my lab's website called Computational Optimization and Innovation Laboratory, in short, COIN. You can find technical reports, and these DNN search papers you can find, and you can see what we have done there. What was the other question?
Yes, sir. So last question is from Dr. Ladit Chandra Saikia. Sir, how can we select the parameters, say population, crossover operator, etc., for a particular problem?
Yes, that's another good question. So one way to do this is to use what is been done in the literature. So there are always lots of recommendations that we have. We tend to use the crossover probability to be a bit high because we want to rely on the mixing that crossover allows. That's really a unique operator to genetic algorithms, and mutation with a small probability. Okay. Now, there are, of course, other methods, like there is a method called I-RACE. I is India, then R-A-C-E, I-RACE. This is proposed by some people from Belgium. And there are other methods as well, which are like a meta learning method where these problem parameters are searched in the upper level problem, and then the actual problem is solved on the lower level, again in a bi-level way. So you are also learning how to set your parameters, the genetic parameters properly by an upper level optimization loop. Okay, so, and there are codes available. You can just embed your problem over there, and the whole system is going to learn and eventually tell you what parameter values it has used the best result. Those are more adaptive, and people are getting used to with such kind of methods. They tend to be a bit more expensive because it's experimenting with different parameter setting before it comes up with a good solution. So if you have the luxury of solving, of using, let's say, thousands of function evaluations, those methods are good at. But I missed out on one problem here that came from the industry, this problem from Ford, actually. There are 8 variables in this, 8 designs, so not many variables, but look at how many evaluations we are allowed to do. Only 61 of them. One was the baseline design that we knew everything about, but we could use another 60 total. So one was given, others only 60 function evaluations, because each evaluations are taking 4 hours to do. So when you have such a restriction, even though it's 8 design variable problems, but only 60 evaluations you could do, you need to use what you call this as the surrogate model, surrogate assisted approach or meta modeling approach. And we also do it with the trust region system, and we can produce very, very good results. I mean, we produce a multi-objective Pareto font, as you see here, and one of our solutions were finally picked for fabrication. So these are, what I'm talking about here is not just theoretical studies, but studies that have impressed them and convinced them that this is something they can even send for fabrication and use it in practice. So you need to be able to, and just using 60 new solution evaluations. So some of those parameter study, they call meta GA or meta evolutionary algorithms, are usually time consuming. So for test problems, which are very easy to compute, you could do those things. But I think if you're not willing to do that meta GA kind of study, where parameters are also learned, then you should fall back to what are the existing values that people use in the literature. So for example, the population size is in proportion to the number of variables. Usually I use 5 to 10 times the number of variables if I'm starting from a random population, but never for industry problems I start with a random population. Always something is available, some knowledge is available. So in that case, you can use, like the billion variable problem, you might think I have used 5 billion population size, 5 times the number of variables. No, because my population was not random. It was utilizing some of the constraints. So I use a population size of 60 for a billion variable problem. It was enough. So it depends on how you are changing your algorithm to what parameters you should use. Hopefully that answers some of your doubts and questions, but you can always write to me if you have further questions.
Thank you, sir.
Thank you, sir. Thank you, sir, for enlightening us by your words of wisdom. Once again,
Thank you very
sir.
much. Thanks for your patience. All right. Thank you. And have a nice rest of the conference.
Thank you so much, sir. Our next speaker is Professor Tanmay Basak from IIT Madras. We'll join at 9:50 for his speech. Before proceed to the next keynote speaker, may I now request Dr. Biplab Das to proceed the program.
May I request Kallanmai sir to just stop sharing the screen, sir?
Yeah, I'm trying to switch off.
Okay.
Yeah.
So thank you very much for
joining. I found it finally here. Okay, it's past midnight here, so I will take off then.
Okay then. Thank you, sir.
Yeah.
Before we proceed for the next session, we have a gap, and in between we have some video presentation on NIT Silchar, including the speech of our Honorable Director, Sir Professor Shivaji Bandyopadhyay. We are thankful from the organizing committee to the publicity chair committee, Dr. Partha Pakre and Dr. Naresh Babu, for putting their effort to edit the video. May I request Naresh Babu sir to please go to the video.
National Institute of Technology Silchar is one of the 31 NITs in India and was established in 1967 as a regional engineering college in Silchar as a joint venture between the government of India and the government of Assam to cater to the country's need for manpower in technology. In 2002, the institution was granted deemed university status and was renamed as the National Institute of Technology Silchar. In 2007, through the NIT Bill Act of Parliament, the Government of India declared the National Institute of Technology as Institute of National Importance. NIT Silchar is currently ranked 46th among all engineering colleges and is ranked 94th overall in India by the National Institutional Ranking Framework (NIRF) in 2020. At present, we have around 200 faculties, 4,000 students, including more than 650 PhD students. NIT Silchar offers undergraduate and graduate programs in engineering, science, and humanities disciplines with 11 departments. The annual intake for the BTech program is more than 880. The institute also offers different post-graduation programs in engineering, science, and management. The institute also has a Kendriya Vidyalaya school up to class 12. The institute has its own kids school. NIT Silchar offers BTech degrees in the 6 disciplines of civil engineering, mechanical engineering, electrical engineering, electronics and communication engineering, computer science and engineering, and electronics and instrumentation engineering under the engineering departments. And admission to these programs is through the joint entrance examination main. The institute SII. In the 4-year program of BTech, the first year instruction is common across all disciplines, in which students are taught the basic courses in mathematics, physics, chemistry, professional communication, basics of computer programming, basic engineering drawing, and basic mechanical workshop. The institute offers MTech programs in all the above engineering branches and MSc degrees in physics, chemistry, and mathematics. The institute also offers MBA degrees in human resource marketing and finance. The institute has received funding in a number of international and national research projects with academia and industry in the past few years. Faculty from the institute have received 4 international projects in 2019 under the Spark program of MHRD with University of Saarland, Germany, Dalhousie University, Canada, Queen's University, Canada, and Goldsmiths University of London, United Kingdom. The institute has also received projects with universities in France and Finland. There are ongoing research projects with SARV, DST, DIT, MEIT, ASEAN, MNRE, CSIR, BRNS, BARC, UGC, AICT, MEIT, CPRI under Government of India. The annual Technical and Management Festival of NIT Silchar, Technosis, is held every year in the month of October. It comprises various events like competitions, exhibits, coding rounds, hackathons, robotic events, and talks from guest speakers from all over India. The annual Cultural Fest of Incandescence is held every year in the month of February. Various artists, singers, celebs are invited from all over the country. The Institute Bakers has put research and innovation as the key focus in the teaching learning activities at NIT Silchar. We have the Undergraduate Research Council to inculcate research activities among the undergraduate students. We work with a vision towards the attaining the Sustainable Development Goals as defined by the United Nations and adopted by the Government of India. All of you are welcome to visit the campus either through its virtual mode or physically also. I wish everyone a healthy and safe stay in your life. Thank you.
Hello, good morning.
Good morning, sir. We can hear you, sir.
Yes, how are you doing?
We are good, sir.
Okay, so I'm there right now and ready to talk. So we can go ahead.
Okay, actually, time was given 10. So, okay, sir, just give us a minute,
Yeah.
sir.
I
Okay.
just saw your email, so I thought that So thing is that I'll be having my PPT as PDF file. Only
Okay,
thing
okay.
I need to know how to do sharing the screen. So can we
Okay,
have
sir.
some practice? That's better actually. That's why I actually logged in slightly early so that we can practice. It will be quite okay when I'll talk.
Yes, sir. Yes, sir. So you listen. Click on the screen, sir.
Yeah.
Then you see at the bottom there are option present now.
Okay, just a minute. I'll just get my PDF file. Okay.
Okay, sir. Okay.
And then what I should do at the bottom?
Bottom right side, you can see sir present now.
Present now, yes.
You click on that, sir.
Yes. Your entire screen, or yeah, I can put my entire screen, right?
Yes.
Okay, I should put allow. There is something is allow or
Yes.
don't allow.
Yes, it has this.
You can see that?
Yes, sir.
Yes, that's it. So everything
Yes,
is fine, right?
Yes, everything is fine. Maybe within 1 or 2 minutes.
Yeah, sure. Please go ahead. I'm waiting for you. You just take your time. That's it.
Okay, sir. Okay, sir.
Okay.
Okay, very good morning to one and all present with us. We have with us Dr. Tanmoy Basak from IIT Madras. Sir, on behalf of the organizing committee of the International Conference on Modeling, Simulation and Optimization, I welcome you to the NIT Silchar. May I now request Professor Dr. Malaya Datta Madam to please introduce our speaker to the guest audience.
Okay. Thank you, Dr. Biplab sir. Ladies and gentlemen, today's keynote speaker of this session is Professor Tanmoy Basak. Professor Tanmoy Basak was born in Kolkata. He completed bachelor degree in chemical engineering with honors from Jadavpur University in the year 1992, masters by research in 1994, and PhD in 1999 from Indian Institute of Science, Bangalore. Also, he worked as NSF postdoctoral fellow on molecular diffusion during 1999 to 2000, and later he worked on air quality modeling and simulation in University of Houston as EPA postdoctoral fellow during 2000 to 2002. Professor Basak joined as visiting faculty at IIT Madras in 2002. He was appointed as assistant professor in 2003 and promoted directly to professor in 2009 at IIT Madras. Professor Basak is recipient of several awards, which includes Young Engineer Award from Indian National Academy of Engineering in 2005, Academic Excellence Award from Indian Institute of Science, Bangalore, India in 1997, Diamond Jubilee Young Achievers Award from Indian Institute of Chemical Engineers in 2007, NASI Scopus Young Scientist Award from National Academy of Science, India and elsewhere in 2009, Dr. A.V. Ramarao Foundation's Best PhD Thesis and Research Award for Excellence in Research from Indian Institute of Chemical Engineers in 2012, and many more. He has supervised 16 PhD and 26 master students at IIT Madras. Till date, He has published over 200 articles in international journals. He also authored 5 book chapters in Elsevier. His publications have received over 5,000 citations. Since 2011, he is the associate editor of International Journal of Heat and Mass Transfer of Elsevier, an editorial board on several international journals. His primary research activities revolve around microwave-assisted processing and computational fluid flow and heat transfer. Now, may I request you, sir, to kindly deliver your keynote speech.
Good morning. Is my screen reachable to all the people? Hello?
Yes, sir.
Yes, sir. Yes, sir.
Yeah.
It is visible, sir.
Okay, thank you. I would like to thank Dr. Biplab Das to invite me to deliver the lecture. And this is my first, in fact, this is my first online lecture in a conference. So I would again thank NIT Silchar to give me some opportunity to deliver the online lecture, which I'm attending first time in my life. So today's talk, since it is a modeling-based workshop, I find it pretty interesting to share my work, what I am working on heat line and entropy generation with the finite element method. So my talk is entitled as Analysis of heat lines and entropy generation for thermal convection with distributed heaters, and this has got modeling aspect, and of course this has got as impact on solar heating applications. Let's move on. I will start from very fundamental of heat transfer, which is natural convection. So before getting the details of distributed heater, solar heating, the modeling complications, I would start from very basics, that is the natural convection. So for natural convection, if we can remember that we have hot wall at the bottom and the cold wall at the top, and for this type of system, what actually happens that hot wall, the fluid from the hot wall actually move in the upward direction, and then which is the cold wall, and what actually happens, the fluid near the hot wall is having the lesser density, and it will actually definitely go up with the buoyancy effect. And while it goes up, what actually happens, the density, the fluid is become more and more denser, so it will start come down. So with that, the circulation cell will complete. So if you look at the screen, you can just see that the basic driving forces, temperature difference, which leading to density difference, and definitely the circulation cell, what I am mentioning, which is actually the natural convection. So the applications of this natural convection, of course, we have the boiling phenomena, boiling water, heating of the rooms, we have sometimes air conditioner, and we have the room ventilation, and the largest application is a solar collector, when we actually we can have arrangement of the solar radiations to be absorbed, and that will be potentially acting as a surface heat source, and with that one can think about the initiation of natural convection, and that can actually, the solar collector is actually like a solar heater, that we need only sunlight, and the sunlight can be kept as a those sunlight can be absorbed, and we can have a potential heat source, and based on that one can think about the heating phenomenon. We'll discuss more for our applications, and we'll see that how the different heaters can be placed, and we can have natural convection. So the modeling work, of course, any work we do, we have some motivation of the work, and which is very, very important. So when I started this work, I was thinking about our basic motivation of the work on differential heating, which was done first of this kind of work appeared. Just I'm seeing showing here that adiabatic bottom wall, adiabatic top wall, and the left wall is cold and right wall is hot. So this type of structure, the configuration of heating is a basic configuration which is called as differential heating. So these papers actually results are published in many of the journals, and people have carried out this type of work, initial phases with finite difference method, finite volume method, even some finite element method. Later on, people did experimental work. And this is one of the problems. People have done so much benchmark. But if I look at the problem, if you see that, right, the consequential development of this problem, which is, we can see that it has unidirectional circulation cells. We can see that this is the way the stream functions, or the stream lines, or the fluid flow paths will be actually developed. And what actually happens if you look at that, the temperature profile, if you see that there are stratification of isotherms at the near the sidewalls and at the core, you can see that these are this part is hot definitely, and this part is cold. So I call this as, if you look at this red light marker, I call this as a situation which is termed as poor thermal management, which is termed as poor thermal management. So if you look at, this is the red marker, I call this as the hot wall. So basically, when you want to quantify how much is the hot wall and how much is the cold wall, generally all these our numerical simulations, they are based on dimensionless units. So what we do that, what has been done in all the works, if you look at this box, this square box, and the square box, all the side is 1. So the area is of course 1 dimensional square unit, and it has got hot wall, which is the unit 1, dimensionless length of it are 1, and cold wall is also again dimensionless unit of 1. So this is one of the ideal configurations what we are seeing in this at the screen, that we have this type of differential configuration. This is the benchmark problem, but there is a problem, is a poor thermal management. Because of this cannot be a good heating combination, because it cannot provide uniform temperature, or we can say that it has got some kind of biased temperature profile, because if you look at this point is hot, at this point is cold, and even this near this wall it is cold, and near this hot wall this is hot. So there are this kind of preferential heating, and many of the applications like food processing, food preservation, some of the other applications, this kind of heating is not expected, not desirable. So what we have to think about, that we have the increase in efficiency of this process by applying the same amount of heating. And that's why the concept at the top, I am saying that discrete heating, or this use of discrete heaters concept, has been invoked for this one. So if you look at the bottom of the figure, this is having hot at the bottom and cold at the top. So if you look at the previous configuration, this is the hot wall, the total dimension, this length is 1 unit. Here it is 0.5, and cold wall is also 0.5. So we have 0.5 and 0.5. So we can see that we can compare these two configurations, both have the same amount of heating. That means here it is dimensionless heating is 1 unit. Here it is dimensionless heating is 0.5. Here it is 0.5. Here cold is 0.5. Here it is cold is 0.5. And these two are adiabatic, which are identical in both configurations. In fact, these configurations I have shown here can be having many discrete heaters. Like we can have in hot the heater, there is a 0.5, we can actually divide to 0.25, 0.25, 0.35, 0.15, and so on. So these are the ways we can have multiple discrete heaters. But I am saying that too much multiple heaters may not be effective, and we'll be discussing that how to optimize number of discrete heaters to increase the efficiency. Now let's look at the qualitative patterns, why we need such discrete heating combination. So if you look at the qualitative profile, I will be showing all the numerical simulations. Here is a glimpse to get some kind of feeling a priori why we need to have such a structure. So if you look at, this is the kind of streamline or the trajectory of the particle, and here we can see that the streamlines are locally oriented. That means we can have the local circulation cells in various points, in various zones. And what it leads to, if you look at the temperature profile at the right side, you look at, of course, there are some temperature gradient near the cold wall and hot wall. And in fact, it's a basic configuration. You can have much better discrete heating combination that I will be discussing later in this slide. So if you look at that, you can see that, of course, there is some zone, maybe we can say nearby 20% zone you should not be thinking about, but at 80% of the zone we can see the temperature is varying from 0.3 to 0.5. This is an amazing result compared to the previous benchmark combination of differential heating. So what we are trying to convey here, that of course if we invoke discrete heating, we can have multiple circulation cells, and that means multiple circulation cells will promote the local thermal mixing, and that will enable the temperature uniformity, which will be having enhanced application in food preservation, food processing, and many other material processing applications. So this is the philosophical perspective of today's lecture, and we'll see that how we implement for different configurations. So as I said, the research perspective is based on the discrete heating, as I mentioned, and for today's lecture we will be considering two cases. One is the fluid media, another is the porous media. So we'll have the different aspects, and we'll see the effect of parameters of fluid media and porous media, and how the discrete heaters would play the critical role. And of course, our research perspectives, these discrete heaters will be leading to thermal management, and we want to investigate thermal management with a tool called heat lines tool. That heat lines is basically like a heat flow visualization. We all know that we have particle image velocimetry for the fluid flow visualization, but heat is invisible. Only thing is we can affect the heat. We can experience the heating effect. What I mean that if something is hot, we say it is, I'm not comfortable, it's pretty hot. But unless you see the, of course, sometimes we can say red hot or something from the burner, But if somebody keeps some hot plate, and if you touch it, you can see the effect is pretty hot. But the fluid flow, you can see that something is flowing, the heat is flowing. What direction you cannot see, only you can see the effect. So the question comes, whether can we see the heat flow? And of course, so far there is no experimental tool which can actually depict that heat flow can be visualized, but numerically it is possible to see how the heat flow can be visualized. So that portion, actually I have done extensive work since 2005 or last 15 years, and you can see many of my papers in Web of Science or Scopus on heat line for the basic background. And I actually developed from the square cavity and then applied in many cases, and we have shown that all the heat transfer phenomena, different temperature profile, can also be explained using a heat flow visualization tool, which is heat line. And the next part of thermal management, which is very important, efficiency of any process. We develop any process, but it should be having very good efficiency. So when we talk about efficiency and when heat transfer and fluid flow is involved, one can think about thermodynamics. And of course, in thermodynamics, all these irreversible processes involve something called, which we all know, that exergy analysis, and that involves entropy generation minimization. So when we talk about, I will talk more about entropy generation minimization, and there we'll see that of course we can have differential system, we can have discrete heater, but entropy generation minimization has to be there to see the efficiency. So of course we can see we are getting very good heat transfer, we are getting good thermal mixing, but how much we are on the entropy generation minimization, that's a good question. So that means you are having a very good process for your comfortable situation. But if you have good entropy generation number, that means you have got optimal generation number. That means your design is complete, and we can, and that is the objective. And of course, our all the simulations will be done for the cavities of the identical area, which is of 1 square unit, as I mentioned in the previous slide. So we have the configuration. First part of our work will be talking about the single heater. So is a square domain. We have this total length is 1, as I mentioned, and this will be 0.5, and the cold overall will be 0.5. It will be 0.25, 0.25, and so this heater could be at the bottom as well, but they are different locations. Now coming back to, so what I wanted, I was not even happy to confine my work in this square cavity. So next structure, actually I took the triangular cavity, and we took the same area. As I said, all the cavities are of identical area, which is 1 square unit. So if you look at the adiabatic wall, it is of 2, length is 2. So basically what we had considered the length of the adiabatic wall 2, and the height is 1. So it is, if you look at the area, it's half into 2 into 1. So exactly 1 square unit, and same thing for that. So what we had, so after that, then somebody can ask question, why you are taking the inverted kind of triangle. So you can see that there are 2 adiabatic walls, one is top and one is bottom, and here so triangle we can have only 3 surfaces. And the situation ideally, what I wanted to do, that we can have but the bottom adiabatic wall, we can have the top adiabatic wall. So in that case we can say that this presence of adiabatic wall, presence of the inclination angle, how it can affect, and we can have an excellent comparison of all the geometries. What I'm saying, that this is like a square is a family of rectangle or the quadrilateral. this you can say that this is the family of trapezoidal, because if you look at the top wall is not there, but top wall is having 0 length. So if you cut the head of the triangle, you get trapezium. So I wanted to show the comparisons between all the family of rectangle, quadrilateral, etc., so that we can actually have basic scenarios of all the cavities, whether the shape of the cavities can influence the heating pattern in the presence of single discrete heater. And in my second half of the talk, I'll be talking about multiple discrete heaters. So that's the overall case studies for this work. So and at the end, what we would like to see that whether we can determine the optimum heating strategies based on, of course, the two concepts what I'm going to address on the heat line and entropy generation minimization. So next we talk about the configuration. So this is a solar heating application. So what we actually do that, this is, you can see that this is the square cross section at the Z direction. If you look at this, is this Z direction has infinite, almost infinite length. This is basically called as semi-infinite approximation along Z axis. So that means that along Z axis there is no variation of the quantities or thermal or any other thermal properties, or the like velocities, temperature, anything. So if you look at this highlighted portion, that is the distributed heater. So what actually we have the solar heater actually at the side walls. This is my triangular cavity type 1, and this is a triangular cavity type 2. And this solar heater, this is actually maintained with a phase change material. Of course, this is a numerical investigation. We have not done experiment, but that this setup definitely would give the experimental insight to the industries. Industries can implement this kind of setup, and they can have the optimal studies based on our numerical simulation results. So, and of course, we'll be maintaining the isothermal condition at the hot wall. So, to maintain isothermal conditions, definitely need to have the phase change material, and which actually also will absorb the heat from the solar radiation. But of course, it's PCM nature. It will have the constant temperature at the wall. So this is the setup, and this was of course some of the part of the work also has been published in the solar based journals. We'll be discussing some of the papers on from out of this work on solar energy or renewable energy journals. So this is the overall setup which will give the insight to do experiment. So this is the computational domain, and as you see that bottom wall is adiabatic and the top wall is adiabatic, and we have the side walls are the heaters. So these are the dimensions. I will be discussing all the dimensions. So similarly, for the triangular type 1 cavity, we have the bottom wall is adiabatic, and we have the side wall, there are two heaters. Similarly, for the triangular type 2 enclosure or type 2 cavity, we can see that the top wall is adiabatic. Of course, side wall, there are 2 heaters, and different dimensions are actually given. So previous slide, what I showed actually for the single heater, this is the schematics, and as I said, this work has been divided within 2 parts, 2 portions. So we have the schematics for the multiple heaters or the double heater configuration. You can see that there are 2 strips. So this is the heater with the longer length at the side wall. At the shorter length, you can see that it could be either way also. It could be shorter length here, longer length here. And these are the sort of combination where the solar heat energy is absorbed, and we want to make sure that this is the part we are having the constant temperature. So a similar approach at the point here. So for the triangular cavity of two different combinations, and this is the overall three-dimensional scenario which can be implemented for the applications and for our numerical simulation. These are the pictures for the computational domain. You can see both the walls are adiabatic, and these side walls are hot, and you can see each side wall there are two discrete heaters or two different lengths. We can at the same length we'll have all the test cases with different parameters in a couple of slides. So you can see this is the triangular cavity of type 1, adiabatic wall at the bottom, and here's adiabatic wall at the top. Okay, so as I said that we'll be discussing about the different combinations. So these are this is the distributed heating scenario, and we can see this is the square enclosure, and we'll be having comparison between square, triangular one, and triangular type 1 and triangular type 2. So we at the first case, which is I will show you. So you have to remember these cases. So it is case 1A to case 1E, and each of the cases we can start of the watt. We have the single heater, and we can say the bottom that is heater of 0.5 and 0.5. We can have slight shifting here. So this 0.5 is shifted, and this is slightly above from the bottom wall. This is the center of the bottom wall, and this is the top wall, and this is the one of the asymmetric combination. So one side the heater is near the bottom, and one side heater near the top wall. So similar comparison can be done for the triangular type 1 and triangular type 2. So configurations. So we can actually see that these comparisons are done in a similar assembly of heaters, and this is one of the nice comparisons because all these cavities having the identical situation. That means we have the same amount of adiabatic wall, same amount of heater. Only thing is that here the cold portion is actually more. So because we need to have the same amount of area, so only sacrifice we have the more amount of the cold wall. In spite of that, we have to see that how the efficiency of the heating may be improved by using the triangular cavity, and some of the results would demonstrate that, and that will justify why we have to go for triangular cavity. So let's look at the next set of the heaters, which will be more complicated, which will be discussed the second part of the talk, which is based on multiple heaters. So we have in the second part of the talk. So first part I would like to discuss like case 1A, case 1B, 1C, 1D, 1E, which is starting from the bottom and slightly it is going to center here, and here you can say top, and here it is two asymmetric configurations. So here the cases are not that many, but you can see that there are two heaters. Okay, so first case you can see this heater is longer, which is 0.35, and this is 0.15. So total heater length is 0.5. So you have total heating combination is dimension unit is 1. For case 2B, it is 0.15, it is 0.35, and case 2C is uniform, which is 0.25. And we have not discussed anything at the top because I will show in the case 1D where both the cases at the top near the top wall, both the heaters, and we know that heater should not be the top portion because generally heating will give the lower dense or lighter fluid, and in the lighter fluid at the top, they will not come to the bottom, and in that case the circulation pattern is very, very weak. So from case 1D we will demonstrate that heater should not be placed in the top portion because that will not give significant enhancement of heating. So therefore, the heaters can be placed near the bottom or the central position. So that would emanate the three cases what we are discussing: case 2A, case 2B, and case 2C in this portion, this part of the study of the distributed heater. Okay, so after giving enough physics or motivation, this is a time to get into the governing equations involving model assumptions. So we have the two-dimensional steady laminar flow for this case, and we have thermophysical properties of the fluid, and the flow fluid are constant except density. Of course, we have the Bosnian approximation with a variation of density with temperature. Of course, we have incompressible Newtonian fluid. No slip boundary conditions are imposed at the wall, and for the porous media, we have the model with the local thermal equilibrium between the solid and liquid phase, which we call as LTE. And we have here, if you look at the continuity equation, the x component velocity and y component velocity are denoted by u and v respectively. And this is our standard continuity equation for incompressible fluid. And we have momentum balance equation, which is the balance equation for the x component of velocity and the y component of velocity. So this is the steady state model we're talking about, which is the convective term. And then this is the pressure term with the gradient. And then we have the Brinkman term for the porous media model. We have the Darcy term, and we have the Forshamer term. So basically, I have written one unified approach of unified momentum balance equations, which will be valid for both fluid and porous media. We can see this multiplied by something with delta, and delta is the switch on-off factor. That means if delta is 1, the entire equation will become the porous media. If delta is 0, it will become the fluid medium equation. In that case, the effective panel number will be substituted by PR. So as I said, the delta equal to 0 is fluid medium, delta equal to 1 is the porous medium. In that case, panel number M will become the panel number of fluid. So we have the energy balance equation, which has the convective term and as the conductive heat transport. So this convective term actually indicates the convection, and which is actually coupled with momentum balance equation. And these are all dimensionless parameter. If anybody would like to know about the dimensionless analysis, so of course x and y are dimensionalized with the length of the cavity or height of the cavity, and with the height of the cavity we have the dimensionless velocity u, v, and we have the effective thermal diffusivity, which is defined with the help of thermal conductivity, density, and of course porosity would come, and we have the specific heat. Theta is actually the dimensionless temperature, which are scaled with respect to hot wall and cold wall, TH and TC, and we have pressure. The parameters already mentioned. This is the effective panel number for the porous bed. We can also have the fluid. For the fluid, epsilon will not be there. It will be simply mu by rho alpha. And this is the Rayleigh number, which is very, very important for the natural convection. And this is a Darcy number, which is very important. We call as modified Darcy number, which is very important for the porous medium. Okay, so now this is a time to talk about the velocity and temperature boundary conditions. So if you look at this is the top wall, which has velocity 0, u and v components are 0, and no heat flux. And this is the hot wall. So all the walls we look at, these are having no slip condition. That means velocity x component 0, velocity y component 0, and the blue wall we have theta equal to 0, and the hot wall theta equals to 1. Adiabatic, the hatchet wall will be having the normal component of heat plus 0, which is typical for the adiabatic boundary condition. Now, this entire problem, I actually don't use any software, commercial software, because always I need to have a focus on the mathematical analysis of a problem. And I always believe that if I have my own computer program, I can do all sorts of analysis, and that would definitely lead some interesting pattern. So what I did, in fact, long back, I developed this solution strategy based, that is the Galerkin finite element method based software, which I have used in many of my research areas. In fact, you have seen that I have more than 200 papers, and all these papers are emanated mostly from the computer program what I developed in-house. So definitely, I would like to spend some time how I develop this finite element method based simulation strategy. So this is one of the typical domain. If you can see at the left hand side at the bottom, that is this is a square domain, and I have shown only the 4 elements, and there are various numbers, the local node numbers, these are element numbers, and node numbers, local node numbers. So each node will have two numbers, which one has global node numbering and one has local node numbering. And you can see and many of the nodes are shared by elements. For example, this node is shared by 2 elements, and this node is shared by 4 elements. So when we do the computations, we need to have information about the nodes, because what we do in finite element method, we first look into the particular element, and the particular element, what we do, that we talk about the differential equation in a particular element. We discretize, and a differential equation become algebraic system. I would like to spend some time, because it's a modeling workshop, and some of the modeling aspect we need to address, I feel, in this workshop. That's what actually I'm spending some time. So here we have typically L is a differential operator, and we can actually write any differential equation as LU equals to F, and U hat is the unknown field which is having velocity components and temperature. So we have the so when you have the differential equation, LU hat equals to F, and we have the error, which is LU hat minus F, which is the error. So the question is how a differential equation can be converted to the algebraic equation. That's the main motive for all these methods, like finite difference method, finite volume method. What we employ, that we convert a differential equation to the algebraic equation, and algebraic equations, even they are nonlinear, they're easy to solve, and based on that we get the solution. And that's the way all the packages have been doing. So we invoke this error, which is orthogonal to the basis function. So basis functions are very, very important in finite element. And what actually happens, that in contrast to the finite difference and finite volume method, this basis function would actually enable any of the domain. If you want to say, for example, you want to have the velocity at this point, or at this point, or temperature at this point, you use the basis function. This is the relationship between the basis function and the velocity. So that means if you know the nodal values of the x component velocity or y component velocity or temperature, you can get the overall velocity components u, v, and theta at any point in the domain. And that's the beauty of the finite element method. Even the domain is irregular domain, doesn't matter. We can have suitable mapping to work on the square domain, and those mappings are very much standard. You please get into my papers, my early papers, which is one of the most cited papers, which is Basak et al. 2006 in International Journal of Heat and Mass Transfer, which is roughly cited more than 300 times, and which is now termed as a benchmark paper. Please look into it. The algorithm of the implementation, we can get some of the glimpse of the implementation of this technique. So as what I was mentioning, that error is orthogonal to the basis function, and which lead the residual equations, which can be solved by introduction method. So I thought to spend some time on the modeling aspect to get some of the objectives of this of this conference. So the post-processing part, so after implementation, we need to, so of course, numerical heat flow visualization is being done by heat lines, and of course, best is the streamline for the fluid flow visualization, and which is one of the standard techniques which we know for several decades for implementation. So the streamline we also implemented using finite element method. So basically, this is the way stream functions are defined. As you all know, that is there in many of the standard textbooks, and this is the differential equation of the stream function, and this also can be solved using finite element method to be consistent. And we have the anti-clockwise stream function with positive sign, clockwise for negative sign. So these are the typical circulation cells I'm going to discuss, and this is one of the quick ways if you want to know how to solve the stream function using finite element method. We can actually formula have the formalism of with the linear operator AD equals to F, and we can have the error which is orthogonal to the basis function, and which will lead to the set of algebraic equations, and from the algebraic equation we can get the stream function at each point. So next we go for the isotherms. So isotherms, we can solve this method from this energy balance equation. We can get temperature, but it's not so easy because we also have to be solved, and there are some hot zones and cold zones. That is the way isotherms actually depict. And but thing is that how heat is being flown from hot zone to cold zone, that is not depicted by isotherms. So that means if I talk here at this portion of the cold zone, heat will be coming. From where it will be coming more? From this heater or from this heater? How much it will be coming? That can be only answered by heat lines, and for that I have to see this slide. So we can see that that post-processing part, we have heat lines and heat functions. So we have the this is the basic governing equation, similar to if you look at this is the equation for the stream function. The stream function is dependent only with the velocity components. But if you look at the heat lines, what we'll actually have, heat line would be dipped. So streamline are dependent on the velocity. Now, if you want to talk about something like analogous concept of the heat line, that's what I'm trying to say, that we must be having something like the quantity of the heat. That means fluid flow is based on the x component, y component. Similarly, heat flow is based on conduction and convection. So there must be having two terms of the concept, that is a conductive and convective heat flow. So we have, this is the conductive heat flow, and this is the convective. So the convective flux and conductive flux will be having two equations, like we had dou psi by dou y and dou psi by dou x. We also have dou pi by dou y and dou pi by dou x, and these two equations can be combined, and we can actually have a generalized equation which can be solved using, again, finite element method. But there is but this heat line is not so easy to solve, because we have some problem of boundary condition. What problem? So look at this situation of the streamline. This equation is second order equation in terms of the stream function. That means we need to have boundary condition for a stream function. So but the advantage of this problem, all the walls, if you look at this psi equals to 0, that means stream function is 0 at all the walls. So that means this kind of problems can be easily solved, which is homogeneous boundary condition. But if you look at this type of wall, what actually happens, unless something is insulated, means no problem, there is no heat transfer. But when you have the isothermal wall, heat transfer will be occurring. So at the wall, you cannot say my heat transfer is 0. So that means no slip, no heat transfer condition is not possible. So in that case, we need to know something called Nusselt number. So Nusselt number has to be computed in a proper manner, and that what actually happens, Nusselt number, point to point, Nusselt number will change, and that means each point will have different boundary condition. So that poses a complicated problem, and because this is basically a Poisson equation, the type differential equation, and for Poisson type differential equation, which is actually very, very sensitive towards boundary condition, and if there is something wrong in the boundary condition, we will get some sort of weird result, or unfortunate solution which will never exist. So we need to have clear-cut formalism based on Nusselt number. So we have a definition of the local Nusselt number, which is we have defined many of our papers. This is the most generalized form of the local Nusselt numbers, that it is depending on the normal component, and this is the having some delta S, which is +1 for cold wall, -1 for whole hot wall. That means when you define Nusselt number, it has got the heat flux and the one direction of heat flux and one direction of the outward normal. So for example, you have heater. So heater means the heater will supply heat in these directions. That means heat will go from this to the cold fluid, and the direction of the normal component along this, so it will be having -1 for the hot wall. With that, we have defined this Nusselt number, which is consistent for the heat flow pattern and the direction of the heat flow. We have average Nusselt number. So what actually happens for this case, instead of having each point the Nusselt number, we actually can formulate this problem, even that by implementation of boundary condition will become too much cumbersome, and each of the junction point, we can actually have the condition for the pi, which is based on the average Nusselt number, and the detailed derivation you can actually look into my papers. Many of my papers have been published in last 4 or 5 years, and we can look in detailed derivation. So if you look at the heat function, why not many works have been there, and why I was so tempted to work on, because of the complicated nature of the problem. And we can see that we have various sort of boundary conditions which are developed based on average Nusselt number, and implementation that is very, very complicated for the very irregular domain, and finite element method easily handle this kind of situation. So again, we have this type of differential equation, and this differential equation has been can be solved using the finite element method. Our papers have discussed all these implementations. So this is even more complicated for the discrete heaters, and this you can see that how this has been implemented. So if you look at the next part, that is the entropy generation part, and the entropy generation, we generally talk about reversible process, which is ideal process, which has no entropy generation. Of course, when you have gradient which is having irreversible in nature, and which leads to exergy loss, and which talk about entropy generation. So if you look at Professor Bejan's book, or earlier Professor Bejan's paper 1983 onwards, which when he started talking about formal entropy generation approaches, we have the entropy generation due to heat transfer, due to thermal gradient, and due to the fluid medium. I have discussed here with the velocity gradients. In fact, any gradient process, no matter the heat transfer, fluid mechanics, even the mass transfer, or any of the gradient processes, according to Professor Bejan, we have the entropy generation. So we have to quantify, we need to talk about something called total entropy generation and Bejan numbers. So let me get into the benchmarks. So this is the benchmark for entropy generation results. and you can see this is the result for present work, and this is the Ellis et al. And similarly, this is the work for present work, and again Ellis et al. Papers, and this type of result, which looks pretty interesting. Scenarios of benchmark, that means all these results actually match pretty well. So in fact, here you have the present work, and we have Deng and Tang for the heat lines, and we can see that this is the first benchmark paper of Deng and Tang who actually presented this, and we have published this work in 2007, and these works actually show that how nicely the heat line works have been benchmarked. So this is basically the benchmark for the fluid media, and we have the porous media. This one of the papers by Professor Nitya, which was done in 1997, and in fact, that time the computational power is not that much, and they used much coarser mesh and infinite element. Even not only much coarser mesh, even they used much more element, much more nodes compared to our nodes, and we actually got much refined and much smooth solution compared to last previous work. So I will quickly show some of the results. This is the standard result of the hot wall and cold wall, the side, and this is the part I show that the stratification of temperature, and these two are the plots for the this is the plot for the entropy generation due to temperature. This is the plot for the fluid flow. This is the plot for the entropy generation due to fluid flow, and this is the plot for the heat flow visualization. That means when you analyze the entropy generation, what motivation you get from the fluid flow, that heat flow, that could be also interesting. So if you look at these zones, that the unicirculation process, and that will actually, so if you look at the heat is actually occurring, transferring from this wall to this wall, and from bottom portion you can actually see heat is actually going this direction and going to this direction. So basically unicirculation process actually responsible, and based on that we have the stratification of temperature, and there are some portions where we get higher values of the entropy generation. So what conclusion you actually got? The poor thermal management throughout this poor fluid field cavity. So this is another example. So previous slide was based on the panel number 0.015. This is the slide for panel number 7.2, and this is for the porous media, and the same thing actually happens. The similar results we actually got, which we see that poor thermal management throughout the porous cavities. So from here so this work we have actually done in detail, and we had the question that can we improve the overall heating pattern, or can we minimize the temperature stratification, or is it possible to minimize the overall entropy generation? So how to solve these issues? And definitely we got the answer based on this PDT. So part 1A, we have the fluid media, which is 0.0157.2, the panel number we discussed, and these are the heating pattern we looked into. So so this is, as I said, panel number 1A, the heaters at the bottom, and this is the panel number 0.015. Their number is 10 to the power 3, and this is the case 1A. So what actually happens, if you look at, we see that multiple circulation cells actually develop as I promised, and you can see that nice temperature arrangement at this point, not much gradient. So that means near, except near the wall, the thermal mixing is pretty high, and you can see the entropy generation of our fluid flow, and this is the way the heat flow is being also. You can see the direct heat flow visualization. So how the heaters are supplying heat. So you can see that this is basically a conduction mode. There is not much circulation, and what we found that CoMSO is smooth, and entropy generation is for the theta is maximum near the hot cold junction, and of course we have end-to-end heat lines, and that actually gives sort of visualization picture. So next is case on a fluid media 0.015 panel number, which is lower panel number for the molten metal, and which is Dirac number is 10 to the power 5, and we can see that at the high Dirac number there are multiple circulation cells. That means the a convection circulation cells of the heat flow are developed, and which is also reflected in the stream functions. And you can see very nice thermal mixing at the middle, and of course it reduces the entropy generation. That I will come in some few slides. So this is also for the case 1A 7.2 parent number, and number 10 to the power 5. Next, we are going to case 1B. So I am just showing some of the fluid media cases. Case 1B fluid media, that is the heater is slightly shifted. At this point, you can see slight shifting of the heater, and that leads much of the complicated flow scenarios. We can refer to some of my papers for that. Similarly, we can see that interesting flow profiles, and that actually gives interesting thermal mixing behavior, which is our objective, and that also reduces the entropy generation. So this is the other configuration for the case 1D, where we have the top portion of heater, and we can see that the top portion is actually not good, because it again gives the stratification of temperature, which is not actually desirable. So definitely those kind of configurations we have not addressed. So these are the final result for the heat transfer entropy generation for the single heater, and you can see that these are the configurations. So case 1A, 1B, 1C, 1D, 1E at the top. If you're in your screen, if you look at, and you can see that the case 1A, where the heaters at the bottom are having the lower average Nusselt number, but if you have more and more discrete heater combinations at the top, it actually increase the average Nusselt number. So if you look at triangular type 1A, type 2, in fact, type 1 and type 2 will have definitely. If you look at the case 1A, that is simple case, you can see the type 1 is giving the larger average Nusselt number. So similarly, Bayesian number and entropy, total entropy generation is one of the interesting phenomena, and you can see that many of the 10 to the power 5 entropy generation is pretty high, and here the number is pretty good. If you look at, it is varying from 9.94 to 19.8, and so of course the average Nusselt number is high, but also it gives the higher total entropy generation. So one has to be careful when you select the triangular cavity. So these are here some recommendations on the square enclosure, which is optimal, triangular type 1, which is optimal, which cases that means which heater combinations are optimal, and so on for triangular type 2. So this is efficient. So this actually talks about the efficient heating strategy, which is based on the lesser entropy generation and the higher heat transfer rate. So next we go for thermal mixing pattern, which is very, very important, how efficient the thermal heating. And we have recommended here based on the cup mixing temperature, root mean square deviation, everything has been computed, and all are computed based on finite element for Madison. And I have shown here how this, what are the optimal combinations can be recommended based on the overall thermal mixing. So next is part B, which is the porous media. For this thing, I will just simply go to the similar kind of results we got, and we have the conclusion based on the entropy generation, based on the cup mixing temperature. So next is the multiple heaters that I have also discussed, second part of our work. I just don't have time, so just show that how the circulation patterns at the center. You see that node stratification of temperature. So that is our main objective, and thermal mixing, everything we have done, and we have also computed based on the porous media, and we have the conclusion for different cavities, square enclosure, triangular type 1 enclosure, and type 2 enclosure, which are the cases are optimal cases. And we have also done thermal mixing for the multiple discrete heaters, and here is the conclusion. So what we found that we have proposed the two different portion of the work. One is single heater, one is a double heater. So single heater, we have shown that optimal cases are there for case 1B and case 1C and case 1E. So, and similarly for double heaters, we have optimal. We have three cases on the case 2A, case 2B, and case 2C, and we have done the we have found that there are some optimal combinations for case 2B and case 2C. So based on the work, Nusselt number is one of the important work in heat entropy generation. So it has been, some of the portions have been published in international communications and heater mass transfer. And of course, these solar heater combinations are published in solar energy, renewable energy, applied thermal engineering, intuition genre heat transfer, numeric heat transfer, all this, and some of the papers already appeared, which is not listed. And finally, thanks very much for your kind attention. Any questions, I would sincerely appreciate. Thank you very much. Yes.
Thank you, sir, for enlightening us by your in-depth space.
Yes.
We can take 1 or 2 questions from
Yep.
participants.
Yes.
Participants, please. Participants,
morning,
any
sir.
questions?
Yes. Good morning.
Myself, Dipankar Bhanjo.
Yep. Yo, how are you doing?
Sir, fine.
Yes.
So, sir, I have one question. Is this analysis is valid for high Darcy number?
Yes, we have done analysis for high Darcy number. But point is that the laminar model has to be invoked. So if the laminar model is not
You have shown
possible,
your result. You have shown your result. You have taken maximum Darcy number up to 10 to the power -2.
-2, correct. You're right. Yes,
So,
-2. You're
more
right.
than that, is it valid?
Actually, more than that, we have done the calculation, is valid. But the thing is that we have to check that locally non-laminar model is possible or not. If the laminar is violated, of course, this model is not valid. So our model is completely for laminar model. And another thing I will tell you, that very interesting thing. So I do a lot of experiments in numerical because I have my own coding and I can always play with that. So once I asked my student, can you do this game when the porous media model will become a fluid flow model? So interestingly, what actually I can actually answer at this point, that if you increase sufficient Darcy number, it will become a fluid flow model. So in that case, I can tell that our code is generic, even it can be handling the porous media and Darcy number both. And you have shown you that if you switch off those terms, we get the fluid flow model, the model equations. And if you have the high Darcy number, you get the simulation results. So the question is how to validate that it has already gone to the pure fluid model. You switch off the term and keep the term and put the high Darcy number, and both should give the same result. In that case, we can always validate. Any more questions on that?
Okay, sir. Thank you, sir.
Okay.
Any questions?
No, madam.
Sir, we have a questions from Dr. Sujit, sir. For force convection, where a driving body force is there in Z direction, how heat lines will behave, sir? This is the questions from Dr. Sujit.
Can you please slightly be speed should be lower because I could not follow the question. Can you please repeat once again? Can you please repeat once again your question? Yeah,
sir.
Madam.
For force convection, where a driving body force is there in Z direction, how heat lines will behave?
Force convection. Can you please repeat once again? I'm not able to follow.
Ma'am, may I request Sujitnath sir to ask the question directly? Sujitnath sir, are you there?
Hello.
Yes, sir. Please answer.
Sir.
Yes,
sir.
Good morning, sir.
Yep.
So my question to you, sir, if for force convection,
we are not doing actually. Yeah.
In Z direction also.
Yeah, actually, this work is
So
for natural. Just a minute. Just a minute. It is for the work I'm actually presenting here, natural convection. So you can actually think about three-dimensional cavities, no problem. This work is only for two-dimensional cavity. So two-dimensional cavity, we have the y direction is the direction because of gravity, and z direction is semi-infinite, that is infinite approximation. If you have x, y, and z three-dimensional, definitely you have to have different kind of model, and that is separate. That is not the scope in the present work. You look in the literature and you can see how to implement it.
Okay, sir.
Okay. Yeah.
Yeah.
Any questions? Any more questions? I think so, sir. There is no questions from the participants.
Okay.
Sir,
thank you.
Once again, thank you very much, sir.
Okay. Thanks a lot. Okay.
Thank you, Tanmay sir, for accepting our invitation in CoMSO.
Okay, thank you. Thanks, Biplab.
Thank you, ma'am, for your anchoring. So I invite all the participants to stay tuned. Within maybe 5-10 minutes, our next technical session will start. Thank you, sir. You can sign out, sir.
Okay, thanks.
Yes, sir. Bye. It's okay. Sure. 11 बजे. Our YouTube link will change for the technical session. So the participants who are seeing or this one lectures in YouTube, please go to the CoMSO site and switch on the technical session YouTube link. Thank you.